life as a teacher. Not right now. Well, we have Scott Gustafson, Senior Architect and Associate at Holly Ellis Devereaux. He's going to talk about a couple of transformative projects he is working on in Mexico and elsewhere. I'd like to introduce himself and walk us through what he has to share.
Hi, thank you very much. Glad to see everyone here today. So, I work for HED, integrated architecture and engineering firm that was founded in Detroit in 1907. We're architects, engineers, and planners with diverse background, ideas, experiences, and expertise. We currently have 9 offices in Boston, Chicago, Detroit, Dallas, Denver, San Diego, Los Angeles, San Francisco. Today I'm going to talk about 2 projects that I'm involved with. Because our company is so big, like 99% of what we do, I have no idea what's going on. It's not a project I'm on, or one of my colleagues is working on, and it's like totally so. So we may have more. I know we definitely have more mass timber experience within our company, but I can only talk about what I know. Within our company, the disciplines we have are planning, architecture, interior design, and landscape architecture. On the engineering side, we do structural, electrical, mechanical, plumbing, and information and communications technology. We also have people who specialize in experiential graphics and signage. So pretty much we do everything except civil engineering. And for many of our projects, a client will hire us for consulting services. The market sectors we serve: community, federal, transportation, healthcare, higher education, housing, mission critical, which is data centers, pre-K 12 schools, science and manufacturing. I work on lots of different types of projects, but primarily I'm in the science and manufacturing, market sector, and also the science. A little bit about me, as I said, I'm a senior architect at HED, registered architect in a couple of places, and I'm also an engineer. I teach in the springtime graduate health and cybersecurity. First project I'm going to talk about is a manufacturing campus outside of Monterrey, Mexico, for a European home appliance manufacturer. So this client is an existing client of HED, for which we've worked with them for over 40 years, but in other businesses. So this project with the home appliance group within their company was the first one. This project is planned to be built over multiple phases. Phase 1 is 9 buildings, about 750,000 square feet. Then we're in Plan Design 2A, which is very hot and warm, but very similar to the climate of southern part of Texas. Monterrey is about 120 miles southwest of Texas. So in phase 1, the main building you see in the middle is the factory. A little portion that sticks out on the south is offices and development laboratories. Building number 2 is the outbound logistics building for shipping finished products out through a rail connection from the south side of the site around that little curve. Buildings 3, 4, 5, and 6 are support buildings that serve the manufacturing site. 7 and 8 are small birdhouses, and building number 9 is a chapter. The center part of the site is planned for a very lush garden that will connect through the buildings, native species and pollinator species. Monterey is right on the butterfly corridor. So the butterflies leave their habitat in central Mexico and come up to the United States in the summertime. They pass right through this area. So our gardens are planted with species that support the This diagram shows the full build out of the site, and because the site is so big, it sometimes, for me at least on these kinds of projects, it's hard to get a handle on like how big it actually is. So our site overall, in both all the phases, is approximately 4 Chrysler buildings, 10 American football fields, end to end. Or if you remember a couple of years ago, the container ship that got stuck in the Suez Canal, we're 3 of the different container ships long. So it's quite a large site. So in this slide, the buildings that are in the bright orange are the ones that are in phase 1. The main factory can be expanded to the north. In the second phase, that would add on another 600,000 square feet. There's plans for another factory that's to the south, and that could also be expanded. In the second phase, the logistics building, which is in the middle of the plan, is planned to be expanded 2 times as they need to store and ship out more material. And then there's space for future factories that can be built in stages under there. Here's a view of the site from the southeast corner, just after they had the initial rubbing clearance. So the main tan part in the middle is the pad underneath the factory. Right in front of that, where we have these sort of bushy green areas, we call them the undisturbed zones. That's where we left the native vegetation that was there, and the roads are only clearing where it's absolutely necessary to build a project. So, as I mentioned, it's a home appliance factory, manufacturing and offices. It's a type 2, or it's a 2-story type 5B unlimited area building. So, because our main uses are business and factory, we have 60-foot clear yard all around the building. We can use this condition for an unlimited area building, which is great because it's going to go from 750,000 square feet to like 2 million, and on the other building, it's going to be like 2.5 million square feet. So this gave our client a lot of flexibility to build the building in a more economical way, and expand the company. So HED served as the planner, the architect, the interior designer, MEP, and landscaping experiential graphics, and we have a consulting partner from Mexico City, Gala Architects and Engineers, and they did structural and civil design. This project, probably at the moment, did not start out as an estimate project, but through the process, something that the designer for the client brought to us, and so they identified a partner from Austria, Haslager, York Timber, and they did facade engineering, assist, prefabricated, insulated CLT panels, and ground floor plan, first level plan, what we call second floor. The top plan is pretty much all the manufacturing is in the middle part of the building. To the far right and far left are internal storage areas, and then offices, development lab, employee dining area, and medical station are in this lower L-shaped section of the plan, and the second floor is more offices and employee lockers and showers for factory workers. So originally, for probably late into the ED phase, we assumed this was going to be an insulated panel building, and we didn't want this to be another gray metal building, so our team looked at ways that we might use color to make the building a little bit more exciting and a little bit more specific, trying to pick up on some textures of traditional Mexican architecture, like lion building in the upper right, building in the middle of the flag is Western Tech University, there's a big history of Dallas, in Mexican buildings and colors of this. So that kind of turned itself into a multi-color facade in 42-inch stripes using insulated metal panels, kind of color gradient. And this idea did not go very far. I think it was, I loved it, I was really excited by it, but I think it was a little bit too vibrant for their taste. And so, this went away and kind of pursued an aluminum colored building for a while. And then, like I said, in the late DD phase, they said, we should do this in timber. And our client is from Central Europe, and they identified Hauslocker from Austria as a partner. So we had some initial conversations with them in, say, October and November, and updated all of our details. And in December, we put out a new package of drawings that Hauslocker used to do their video. So, for us, it was very easy. We first made some texture map. Now we have wood building, and then once that starts made, lots of wall sections. These are all handful. Lots of details. These details look kind of generic because at that time I didn't work on a master building, and I kind of understood the system, but I didn't know a lot about it. But we knew that through our intense collaboration with our timber partner, that we would get way deep in all of the details. So, as I said, Hauslocker received a package that they could do their final bid on in December, and that was finalized in March. The client said, great, we hired them. We need you to come to Austria next week for a workshop. And so my coworker Jeff and I bought some airline tickets. 4 days later, we flew to Vienna. Hauslocker employee picked us up at the train station, drove us 4 hours west to deep in the mountains of Austria, to Hauslocker's main facility in Texas. We did a quick tour through their CLT manufacturing facility. They had already built a mock-up for it that was stuck on the wall. And then our team here, our architects and their engineers and compliance architects and engineers, we all retired to a tiny little conference room for 3.5 days of very intense sketching and collaboration on pretty much all the detailed features. So, as I mentioned earlier, this was not originally planned to be a CLT building. And we're using CLT just in our facade system. I should have mentioned this earlier. The structural module of our building is 24 meters by 18 meters, which is about 80 feet by 60 feet. And the building is about 40 feet tall, and the length of the package is like a quarter mile long. So that's a big, long facade in a dusty area that gets a lot of wind pressure. So when it was an insulated metal panel facade, we would have had horizontal steel girts about every 6 or 8 feet to carry that load. When we changed to the CLT facade, those intermediate girts came out and we introduced vertical wind columns every 6 meters, which is about every 20 feet. And we ended up analyzing the CLT 6-meter work. That worked out great because then they could put 2 lengths in a shipping container, just shy of 40 feet. We originally thought that the building would be modularized vertically in 2.5-meter sections, which is like close to 10 feet. That was cut down to 2 2/4 meters, which is 7.4. That could also fit in a container. Just like an IKEA piece of furniture, and playing around boxes. That would be most economically because they can ship. They can send out shipping containers from the factory to trains. So after many days of thinking through all the details, we had a strategy for how we were going to work through the shop drawings all the way around the building. For this building and the other buildings on the campus. So basically we have two wall assemblies for the exterior of the factory. It's 100mm CLT, 5 layers, about 4 inches, 2 inches of inner wall insulation, and then a range of cladding that's about 50mm. No. Driver, yes. So, Hauslocker worked with the Technical University of Graz to test different species of wood in an environmental chamber, where they ate simulated 30 years of exposure in the monitoring climate over a 10 to 12 week period. And so then they came to us with recommendations of like, we want to use this kind of Siberian larch, or we don't want to use this, we want to use this. So that was, research that they found. But our client did not want to do any maintenance on the building. So it's just regular wood on the side with an anti-termite coating. Just anti-termite. So, as Michaela mentioned earlier, coordination with your fabricator is really important. So, when Jeff and I came back from Austria, that kicked off a series of weekly meetings between our Mexico City team, the team in Austria and Germany, and the architect, myself, and other people in our office, where we met with Hausblacher group. Yeah, once a week for probably 6 months. And, hundreds and hundreds of sheets of shop drawings, because we were working on the factory in section, so they could continue their production while we were kind of solving the next piece. These are really crazy drawings. Some of them are like 24 inches by like 2 feet long, and super detailed. Everything's down to like the millimeter. We had so many discussions on, can you move this over 3 millimeters? We're moving it right to like the width of the carpenter's thumb. I'm not changing the Revit model. You fix it in shop drawings. Yeah. So another interesting part about this project is the owner elected to bid out different scopes of work in different sequences to totally contractually independent contractors. So this steel structure was planned to be able to take those skirts. We got some precast walls at the base. Those were already set on foundations that were outboard. And when we decided to switch to the CLT structure, all of that got sucked inward, so it just runs across the face of the columns. But we had to change all of the precast. Most of the precast panels hadn't been built yet, but they had to be detailed for their new position to sit on the grate beams, which you can't sit here, power caps. And then we developed a system of steel plates on the steel columns, which we call the ears, to be able to attach the CLT panels. Because a lot of the steel had already been built or was quite so far along in fabrication in the shop in Mexico City, a lot of these pieces were wheel welded. And then later on, as they were starting to do more shop welding pieces, they had that individual steel. This picture here is a seismic joint between two sections. The picture on the right is Adriana from Hotel. So here we have some of the elements from Hausblacher delivered to the site. The CLT panels and the mineral wool insulation and the black weather barrier were all installed in the factory in Austria. The CLT cladding elements, the vertical pieces and the back battens, are aligned to the horizontal elements within the insulation framework, so they're just stacked together. And then there are foam joints or foam tape between these teeth joints and the CLT panels, and another compressible joint is vertical. So each panel is fully sealed, air sealed against the adjacent panel, and then they just tape the seams from both panels. The green screen cladding parts were prefabricated in elements that are about 1 meter or 40 inches wide, and the upper section here is maybe about 25 or 30 feet. The lower section is about 10 or 12. There's a reveal joint that kind of follows it down to the building. But they were able to crane these pieces up off of the pallet, get it around the building. There was 2 guys on the roof, 2 guys with these cherry pickers. They'd shim it, level it, pull out their screws. So each panel went up in about 5 minutes to do a section. So before this, I always thought of these types of facades like they're quick enough individual stick by stick without anything. Nothing would have been close to alignment. So this prefabrication for this kind of. This project is industrial grade, both in the facade and in the CLT. So not the fancy grade wood, no concern for where the knots are. But I actually think that it's really nice because it gives the building a lot more texture and character than you would normally expect in an industrial building. And even from like a far distance, you can kind of read the gradations in color. And you can sort of see right in that panel, there's a finger joint where two pieces come together. So even within a vertical strip where you have different boards that were finger jointed together, you have different grain textures, and it adds a level of variety and interest at the human scale that I really enjoy. The wind columns come up past the roof to support the back of the parapet. This column, the cap on it is lower down, so the parapet cap can go over the top. The back side of the facade has just a simple corrugated metal panel that covers probably the top 3 feet, and then the roof membrane would lap up and terminate just at that one joint over here. Inside the factory, as I mentioned, we have some precast walls and base that is a requirement of the client, and then we have CLT exposed at the top. So even though it's an industrial facility, I think between the wood and the smoke vent skylights we have, it really opens up a bigger and most factories probably. All right, I got like 8 minutes, and there's not many slides in the second one, so I'm going to stay right on. This second project is for another long-term customer of our office that has multiple sites around the country, and they develop prototype building solutions that they can implement at multiple locations in a certain context. So we have previously done a study for them to take an office building prototype and convert it from a precast wall and steel structure design to a mass timber design. Their goals were to reduce the carbon footprint of the building, to be cost and schedule neutral or cost and schedule positive versus the baseline. And in the first study, we only looked at mass timber roof and structure, and the exterior was going to be insulated metal panel, because that's something we're familiar with. In the second project, and another way we wanted to talk about today, we were able to convince them that we could use a lot more wood in the exterior. So in this case, in this project, we only went to pathway schematic design for this study. H&E was the architect, and Holmes Engineering from San Francisco was our structural partner, and Therapy partner. So in our client's language, they would call the first office building we did a single region. This would be for a site where there's more people, not exactly double the size of the building, but they call it a dual region or a multi-region. So the first one, 60 employees, 60 full-time employees would be there. You could have up to 44 part-time employees or consultants that would come in, and then this building has the dining hall for everybody that works on the campus. So we have kitchen space and seating for 245 people. In the multi-region version, it's basically double all of that. And then in the third image, it's kind of showing that like just because we're doubling the number of people doesn't mean that every room in the building is double. So this kind of simple diagram, which parts of the program actually really grow because of doubling the headcount. Kitchen gets a little bit bigger, we need a little bit of additional meeting space, we need a little bit of additional open office space. The original idea from the client was like, hey, we've already designed this building, let's just make it bigger. But it would have made the footprint of the building kind of steep. It could just kind of grow out of these selected areas. So we ended up kind of redesigning the whole thing to shift some of the program pieces of it. So the open office went from the south to the west. That allowed it to stay as one main piece. Get the building a little bit deeper, and then the kitchen and the servery, that also comes moving down. And then we have an internal corridor that kind of loops all the way around the building to connect those spaces. On a plan, diagram. So main entrance in the front, sort of recessed porch with electrical equipment, kind of all standardized in the right-hand corner of the kitchen. There's a little courtyard notch in the back, which you'll see in the window, and then all of our HVAC equipment is measured in the front. These pieces are to the right, really serve the kitchen, and the other air handlers serve the space. The original building, the baseline was a 30 by 30 grid. This one was changed to a 15 by 30 grid. We use 15 because the roof structure is Frere's nest plywood panels, and so they can span 15 feet. We introduced these 8-foot wide zones, which we call the HVAC spines, so we can take our glulam roof beams down from 25 inches to about 8, and that allows us to kind of tuck our main east-west ductwork up in there, and then we just have trunks single phase to keep the distribution. The exterior wall is a prefabricated assembly, not using mass timber, but using a dimensional lumber framework. So going from the outside in, the outside is a 1x4 mesh cladding, very similar to what we have in the project in Mexico. NMB is a UV barrier, UV resistant weather barrier. NMC is a prefabricated insulation, mineral wool, or no, in this case it's wood fiber insulation in a wood framework, again kind of aligned to the lower map part A. And then the main core of the building is 2x8 framing with wood fiber bad insulation, and then the items D and F could either be 3/4 inch plywood or 3-layer micro. And then this sits on a insulated precast base we put up on the ground. Not a whole lot going on architecturally. It looks like a horizontal or it's vertical. We change it in some places to break up the character facades, and then just kind of add a little bit extra layer of texture here. This is in that recessed porch I mentioned. When you come into the main lobby, exposed glulam beams, exposed plywood ceilings, exposed CLT on the wall. In the office spaces, as mentioned earlier, we have that main trunk for the HVAC distribution, with very simple lines coming out in bag lighting. We only went to like halfway at SD in model all the fire sprinklers. At the time, we were looking at the garbage that goes up in the ceiling, but we didn't talk about where we're going to have to plan that within our system. Courtyard in the back, with additional gathering space and dining space for the employees. Thank you very much. Any questions? Yes, sir.
How did that switch to the
You know, actually, one of the things that drove the client to switch from insulated metal panel to CLT is that it was less money. Our client, this is true maybe for a lot of European manufacturers, they're afraid of home insulation because they're worried about fire risk. So our building, the only home insulation we have is something like garage doors, and otherwise it's mineral wool on the roof and mineral wool on the walls. The insulated metal panel manufacturers really only make mineral wool IMP for 2-hour firewall conditions. So it only comes at one thickness, which is 4 inches, which is more insulation than we needed, and it weighs a ton. So, and it's mostly, it has to be made by hand, whereas our foam insulation panel is much faster. So it was actually material savings, and then theoretically it would have turned into a schedule savings if our steel contractor had been more diligent in their delivery of materials. So there were some difficulty in the sequencing in the project, but that's also because the owner thought this is what different people had no real reason to.
Supply chain?
Hmm?
Supply chain?
Not really supply chain issues on any of the materials, but it was more production problems in the non-wood parts of the building that kind of caused issues. Yes,
So where you had the connections on the steel and you were welding them?
yeah,
Did you find they didn't quite fit? So I mean, we did
Yes.
steel to steel connections and the wood, the steel bends as well, and so it was designed to be a certain size on the wood.
yes.
And it slightly moved, and it wasn't, I mean, it was like millimeters, but you had to sand some wood off to get it down in a hole for steel hole.
Yeah, well, say the right side here was horizontally slotted, the left side here was vertically slotted. For a little bit of that tolerance. But yeah, Germans, Austrians, they're very precise people. You know, they're like, we're talking about, we need to move this over 3 millimeters, which is like 16th of an inch. And I was like, the standard tolerances for steel construction in the United States on calling this all is like plus or minus 3/4 of an inch. And with this contractor, it's going to be like even more. So I would always say to people like, this is not the Museum of Modern Refrigerators. It's factory. It's really long. Like if the facade has a little bit of wafer to it, nobody's going to notice. But there were some field construction tolerances that we had to deal with. It was the work. I think the Europeans expected it to be much more.
I thought it was really, and maybe this is like for the students as they're thinking about design. I thought it was really interesting. You started with the position like, okay, this is a big facade, we're going to use metal panels and we're going to use color to break it up. And then it seems like the wood, as deployed, accomplished your goal better than you would have done for the metal panels.
Yeah.
So now in future projects, are you starting back with those wood?
I'm going to propose wood on record.
So, this is Pat, that question for Pat, you're a convert now.
Yeah. Well, you know, I have an interest in wood architecture and sustainability in general. And because I've had the opportunity to work on these two projects with others, well, I'm not an engineer by any stretch of the imagination, metaphorically or legally speaking, I have a better sense of like what's possible. And so I want us to get to the point where we propose wood as our structure system to our client from the beginning. You know, I was fortunate with these two projects with these clients that they were pushing me on. You know, our office is very comfortable in concrete and precast steel, and I want us to be able to go, this is what we would do in timber and do that from the get-go.
I think the important part, and this is something I deal with in my faculty or my administration at Clemson, is when you have exterior wood, it will change color, it will get dirty, and don't expect it to always look the same. So it's those pictures in 3 years of that exterior, they'll be darker and dirtier because wood holds moisture.
Yeah.
And as dust blows in the air, and I think you're all aware how much dirt is out there blowing around, it will change, it will not be that pretty. So just help your people understand.
Yeah, somebody mentioned thermally modified where you can always get fresh cavity samples from your supplier.
Yeah.
I have pieces I left out on my desk next to 3 years, so I can show people this is what it looks like later. So I try and make my texture maps look like the building's a little bit older. To be able to mitigate people's expectations.
Absolutely.
You know, on this building, I know I gotta wrap up, also on our project in Mexico, we kept the bottom of the wood about 2.5 feet off the ground.
Perfect.
So we don't have splashback from the rain. It's gonna discolor as well. And also because this is the termite area, even though we did termite treatment on the wood, you know, the termites still in the channel going up the concrete, so we got a couple of feet to be able to see them before they make their way.
And this is a relatively low humidity area.
Yes.
Hello, everyone. My name is Elizabeth Hartman. This is Ethan Schilling and Stephen Schilling. We are all architecture seniors at Lawrence Tech, and we will be discussing mixed-use structures through the lens of mass timber construction.
So just for a general overview of mass timber, we've kind of gone through most of this. The things I'd mostly like to highlight is just it has strength, durability, but also flexibility. It can be used in linear, but also curved shapes and formed custom assemblies, as well. The benefits, mostly being the quicker, more efficient construction, having a lower cost, and being able to create more sustainable buildings. And so then just for the main types, we've seen CLT and GLT. Those can pretty much be used in any part of the structure. Then NLT and DLT, those mostly you might see with floor and roof decking.
Mass timber has a very interesting history. Prior to the 19th century, wood was the primary construction material, but as was discussed earlier today, following the novelty of steel and concrete construction, it really lost popularity and the public favor. And mass timber didn't really start to be developed until the 1980s in Austria and Germany. Following that development, it began to spread through Europe and then eventually started to gain interest in the United States in the early 2010s. Since then, mass timber has had a lot of very rapid development in the United States with the introduction and modifications to its inclusion in the International Building Code and a lot of landmark constructions happening back to back. Looking forward, we're seeing more research being put into both softwood and hardwood use in mass timber construction, how we can push the limits of what we're currently using, and how hardwood can be introduced into the constructions.
And then for the different types of tree species used for mass timber and the types of wood, these are just 6 of the main types. Mostly going to use softwoods, as we've talked before, and need them for strength and durability. And if we look to see where they are in at the map, you'll see spruce pine fir, southern yellow pine, Douglas fir, hemlock fir, Alaska yellow cedar. They all kind of nest over each other in the Pacific Northwest. And also red pine. This one obviously is going to be within those SPF forests. But this is also one important to at least Michigan because as the research on mass timber in Michigan is happening, it's one that they're beginning to source locally within Michigan and seeing how viable it'll be for future use.
And then if we overlay all of the manufacturers over top of the wood type, we also put our custom studies that we will be looking at later on. You can kind of get a general sense of how these are laying out in the manufacturers are.
For our manufacturer, we chose to examine Element 5 for our primary source. Element 5 has just started their ventures into mixed-use constructions of supplying materials, with their flagship project being Coda Detroit, which is actually just a little bit up woodward from here, where we are right now. This is a hybrid construction with mass timber and steel elements, and it's really the first look that we're getting at how Element 5's products in particular can be used in mass timber constructions. And we can see in the renderings that they have provided for their plans of how they're letting the mass timber elements shine through and really being a defining feature of the spaces.
So Element 5 comes with about 5 different products, a very diverse repertoire here, but they do have the standardized CLT. What's interesting about their products is that they're able to use them for shear walls and for shaft walls at 5 ply or more, just for the fire rating at 5 ply. And then they also have a pretty standard glue lam, spans up to 52 feet. They also do the visual versus non-visual appearance here. They have clips, which is their cross-laminated insulated panel. It's able to suit any amount of insulation that is required from the project in any different region. What's interesting about all of Element 5's products as well is that they're able to mold or cut out anything that is needed for wall openings, windows, and doors. They're able to install that inside of the factory. And then box panels are basically 3-ply CLTs stacked between a glue lam runner. This is particularly really good for MEP integrations as well as insulation requirements. And then nano CLT is really like just perfect for interior hard surface applications. Anywhere that you want to bring out a little bit more wood in your project, such as stairs, cabinetry, any surfaces really. And then we also looked at a secondary and a tertiary manufacturer, Sanson and Simpson Strong Tie. They're really able to enhance the mass timber appearance within our spaces and functionality with their concealed beam connectors and construction needs. As well as for Sanson, the stains allow for exposed wood inside and outside.
As I said, we are a mixed use construction type or occupancy for our structure. The IBC recognizes 10 various occupancy types, and mixed use can include any combination of those occupancies. As such, for code considerations that are taken in relation to the occupancy within the structure, we are always going to be taking the most conservative of the occupancies that we have listed in our program. We are looking at between types 3, 4, and 5 for mass timber constructions, and then with each of those subcategories, subtype A for elements that require fire protection on all combustible elements in the building, type B for fire protection required on most combustible elements, and type C where no additional fire protection is required for those combustible materials. So we've looked at how the height or allowances change based on the occupancy in the structure, even within a single category within the International Building Code. And then looking at some of the fire rating information, how that varies between both the construction types and the individual members that occur within our structures.
For structural grids, you're pretty much only looking at two types, square and rectangular. For square, it's going to be typically ranging from 20 to 30 feet. Structurally, they can go larger, but there's really no benefits to doing it because once you do that, a lot of the beam sizes become very, very large, which decreases headroom. There's going to be economic issues at play with that as well. For a rectangular, they'll be anywhere from about 12 to 20 feet to 20 by 32 feet. And then these ones too typically will not use intermediate beams. This is mostly for MEP integration. It makes it a lot easier for them to do so. Now just as a general guide, you'll see the tables below are just kind of things detailing different member sizing based on panel size or span. But overall, as with everything in construction, the goal would be to increase efficiency, minimize waste. The easiest way to do this would be to pick your manufacturer early. That's also not usually always possible because it also limits your options. So just know that most manufacturers would tend to be on a 20-foot grid size, and that way you can kind of size up your bays to doing that and making sure that if you had to switch between, you're not going to have to redo your entire bay. And then when we look at carbon emissions and the carbon footprint, about 42% of all CO2 emissions come from the built environment, with 23% of all emissions being from just 3 materials alone, with 11% being steel, 10% concrete, and 2% aluminum. So that's where wood's very important, as it can help reduce those emissions as it stores carbon instead of releasing it back. And up to 26.5% of those emissions can be reduced just from using wood over steel or concrete.
One of the main draws to using mass timber as a construction material is the life cycle that is associated with mass timber products. There are two primary segments to the life cycle of mass timber, having the growth cycle from when the tree is first planted up through its harvest once it's reached maturity, at which point new trees can be planted in its place, and those harvested materials can be brought into the manufacturing facilities to be milled and fabricated into those individual panels and beams that will be used to create a kit of parts for construction and then be assembled on site for the desired project. Wood also has the very unique capability of being able to be disassembled after the building that it was originally used for has served its purpose. And those individual members are either able to be recycled back into new projects for use in the same manner that they were originally used for, or mulched down to where they can be used in various ways, such as in landscaping or as a biofuel. All of that leads to wood having a very efficient circular economy. You are getting a very good return on the raw materials you're putting in with minimal waste of being dumped out of the system without any sort of recycled use throughout its lifespan. Wood also helps with the overall energy efficiency of the structures. Wood has a low thermal conductivity and higher thermal insulation factor compared to steel and concrete, which helps to reduce the overall operational energy requirements of the structure and also helps to reduce the heat loss through thermal bridging. And due to the precision that is available through mass timber production methods, you're able to create much more airtight connections than with other construction methods, resulting in fewer drafts throughout your structure, again, helping with the energy efficiency. In addition to this, as has been discussed a few times throughout the presentations today, biophilia is a very prevalent topic being discussed at the moment. And the presence of wood is proven to help reduce the stress, increase concentration, and improve overall moods of the occupants within the space. Wood as a material holds strong connections with nature and is commonly associated with warmth, beauty, and tranquility. So the presence of exposed timber products within your spaces helps to enhance the overall experience within that space. And then as Pat was describing earlier, having a high demand for mass timber products helps to achieve sustainable foresting practices. As the demand for these products rise, companies are incentivized to invest in proper forest maintenance so that they are securing their profits down the line and their materials that they're able to capitalize on. They're maintained responsibly through practices such as forest thinning, keeping up with planting new trees, and that system also helps to improve the carbon impact of those forests with higher rates of carbon sequestration occurring in the earlier years of a tree's life cycle, and thus increasing the overall carbon sink potential of the forests.
So as we look at transportation, we see that erection drawings or sequence drawings play a very crucial part in the first aspects of looking at the transport, to where you get your mass timber manufacturing components, and then you're getting them into transport, and you have to decide what is most economical for transportation, whether it be the truck bed, the freight train, or the cargo boat. But what's most important is that you're protecting these mass timber components from the UV, the rain, or ponding that can happen. And then if all goes well and everything is on track, you should be expecting deliveries and installation per the erection drawings. Save a lot more on money and time.
As everyone knows, there is a ton of coordination that's necessary for any construction project. And with the mechanical, electrical, and plumbing integration, this is no exception. As Ethan mentioned earlier, Element 5 in particular has their box panels that can be used for the integration of their MEP systems. But more in general, as mass timber structures typically have very strong directionality in their structural bays, in many cases, the MEP systems can be run parallel to those structural members, allowing for very minimal crossover needed between the systems. When those crossovers are necessary, though, there are a few methods that can be used to remedy this. You can drop MEP systems down below the structural members, have penetrations pushing through them. You can run the MEP systems through chases above the beams but below the panels, or run them between gaps that exist between the panels there. You also have the option of running the MEP systems above the ceiling panels, either under a raised access floor or embedded in topping slabs over that mass timber panel. Each of these methods obviously has its own set of benefits and constraints, and each one would have to be examined to determine what is the most effective strategy for a specific project.
And then as we look at user comfortability through the acoustics of the space, we can tell that CLT doesn't have the best STC ratings for our mixed use typology. So in a lot of rooms, we're seeing a deficiency in STC ratings, but there are multiple ways in which we can go about changing that with some of the standard assemblies here, get some higher ratings even in the 50s or 60s.
We've examined a wide range of precedents throughout this research, one of which is First and Fourth, designed by Pivot North Architecture in Ketchum, Idaho. This is a hybrid construction with primarily mass timber, but also some steel elements throughout the system. And one of the shining characteristics is their use of mass timber as their finishing materials throughout the structure. For the exterior cladding, they used shosugiban panels, which are charred on the outside, increasing the overall fire resistancy of those cladding panels, while also helping to keep bugs out of the structure. And then, as you can see in some of the other images on the screen here, they are allowing those CLT ceiling panels that they used throughout the system and glulam beams and columns to be some of the defining features within the space.
And then 111 East Grand, this is in Des Moines, Iowa. It's by Norman Monson Architects. Big highlight of this was how they did the construction process. They used Haslacher Norca for a glulam post and beam structure, but they also did structure craft for DLT. This was one of the first mass timber buildings in Iowa and one of the first in North America to use DLT. So they faced a lot of issues when it came to the code approval process, getting it through city codes, as well as just with overall coordination. That's where they used the integrated project delivery. And they were able to get the overall structure, most of it up in about 7 weeks, which is 6 weeks faster than normally would have happened with steel or concrete. Then the Soto, this one's done by Boca Powell and Lake Flato Architects. They did the same thing structure-wise, so they had Haslacher Norca and Structure Craft with GLT and DLT. This one, though, was one of the first buildings to employ a brick masonry facade with mass timber. So a lot of the issues they had, as you can see with the detail, was they need very intricate detailing to kind of deal with the different forces that come from having masonry and timber and trying to connect those all together.
So another precedent that we looked at was Framework out in Portland, Oregon, and it became one of the first fully mass timber high-rise structures to be approved by code back in 2018. Unfortunately, it is on hold for building, but the structure is pretty fantastic. It uses a 9-ply CLT shaft wall in the core, and that will deal with a lot of the seismic loads that Portland deals with, and also the fire rating has been extensively studied as well for this project. For 619 Ponce, it's a retail and office space over in Atlanta, Georgia, and what they've really focused on and done well in is the sustainability aspect of it. All of their sourcing and manufacturing has been right around that general area within the state. Another thing that they've done well with is the user comfortability, looking at the acoustics and then MEP integrations here using their raised girder purlin system. They were able to put the MEP through the underside of the floor system, but then above the girders.
And then finally, we looked at the offices at Southstone Yards. This project is a collaboration between Gensler and Duda Payne Architects down in Frisco, Texas, and is part of the larger Southstone Yard developments, which will, upon its completion, contain 15 structures across 3 acres of activated park spaces. The mixed-use office building is a shining characterization of how flexible your programming can be within mass timber constructions. They were able to keep their entire structure very open, especially on the upper levels that will be used as office spaces. As you can see in the floor plans up in the top right corner of the screen here. And by keeping all of their structural elements very open, as well as using a raised access floor for all of their MEP integration, they were able to create a large degree of flexibility in which the tenants of the spaces can choose what arrangement works best for them and include and add in partition walls that can be modified depending on whatever tenant is currently occupying that space. Throughout each of these precedents, we have found a lot of lessons and just shining characteristics that are showing the capabilities of mass timber construction, and we'll be sure to keep each of them in mind as we continue through the design phase of this project. Thank you.
Thank you very much.
Thank you, guys. I'd like to welcome up front Nate Sosen. He's our structural engineer expert who is a principal at Thornton Tomasetti's office in Chicago. He has worked in a multitude of project typologies, and for the last 12 years has been teaching at Masters of Architecture students in the program at the Art Institute of Chicago. Echoes. I will use this. Well, can you guys hear me if I don't use this? Yeah? Okay. So I'm probably going to be pointing with it. So, I was saying a couple of things I said earlier was that number one, I have way too many slides. Number two, I also like how there's a lot of overlap between the talk. It's not like kind of a lapping, not a complete overlap, but a bit of continuity. I've seen some of my slides up here already, so that means I can go through them real quick. So, quite easy. What I'm going to try to talk about today is how one size does not fit all. Everyone who has been up here has talked about the variety of systems and ways to work with individual systems. What we do at TT is we try to synthesize all of the technical criteria and turn that into a successful project. So, Gordon Thomas said he got 1,700 people. I think we might be closer to 1,800 now. We've worked in 150 countries. We've got 45 offices on 5 continents. So we are a global company from a really nice perspective. In North America, we have offices in Ottawa, Mississauga, Toronto, and north of the border. And then we have a number of offices here in the U.S., Milwaukee, and Chicago. We kind of close our Great Lakes offices. We handle everything from Minnesota to Ohio, kind of locally, and then obviously we work locally all over the world. I'm based out of the Chicago office. I thought I'll just talk about biophilia and how it feels to work in a timber space. Beginning of this year, we moved into a timber space, and I can say, from personal experience, it's so much better. I looked at Steve Sandro's last building that he built. Previously, I was there for 12 years. Beautiful lobby, beautiful facade, super cold, sterile. So moving in from a museum building to this building was super comfortable. It's a heavy timber building, not a mass timber building. We did include some blue lamb on sort of this pin-up wall. The color there was based on when you temper steel, the different colors at different temperatures, when the steel sort of glows. We have a nice sort of biophilic mural that was we commissioned. Anyway, it's a really nice space. I will say we do have all of these guys are active white noise machines, essentially, active acoustic damping, because timber spaces do not have the best acoustics. So rather than doing sort of a passive ceiling through the space, we did an active white noise. It works pretty well. It actually broke down for a week. Everybody noticed it was kind of weirded out if it's still running. So you don't notice it when it's there, you notice it when it's gone. And then really quickly, TT, a lot of folks know us as a structural engineering company. I'm a structural engineer by trade. We do renewal and adaptive reuse. We do facade engineering, sustainability consulting, construction engineering. We do a lot of protective design and security, that blast design. Michaela talked about embassies and using wood. We do a lot of embassy work. So all this means that we all look at projects from multiple perspectives internally as well as externally with our clients. So one of the things I love about it. A lot of you folks covered the sustainability aspects of mass timber. So I got really just 2 slides on that. Slightly different perspective, same message. So global building stock is doubling by 2060, which is like 2.5 trillion square feet of new floor space, which is like building a new New York City every month. We're building a lot of buildings all over the world, so we have to build them sustainably. At Gordon Thomas Study, we focus a lot on embodied carbon because a lot of you do are less focused on the life cycle. We're really more on the immediate, like what can we do in the next 5 to 10 years to arrest this crisis? And then, timber also has the benefits of you can deconstruct it and do everything. So you guys have seen another version of this slide already: steel, concrete, aluminum, the big boogeyman. We do focus a lot on low embodied carbon concrete, cutting the embodied carbon in concrete by half or by 2/3. So you'll actually see some of the systems we've been working with are hybrid that have really low embodied carbon. So
So, you know, one of my least favorite terms as a structural engineer is like the optimal structure or optimized or most efficient. It's such a loaded term, and to me, what an optimized structure is, number one, what's the building going to be used for? Obviously, building codes and life safety are important. Architecture is pretty critical. I mean, we all want to be in well-designed buildings that, you know, we're proud to have and we're proud to work in. So that's hugely important to me. Occupant comfort, and then you get down after all of that, all of the project brief is sort of presented and digested. Then we get into material properties and fabrication and erection. How do we use the material properly? So a lot of what you're going to see and a lot of how we approach mass timber is what is the right system for the job, from who's using it, how they want to spend, what message they want to send, who's going to be fabricating it, what species we're using, etc. Just quickly, the kit of parts, again, clearly all of the students really know this really well, so I'll go through this quickly. Different species have different material properties, they have different colors, they have different visual appearance, and then the finish of the CLT panel also comes into play. There's architectural finish and industrial finish. And Michaela, you can put your earmuffs on for a second, but when you get, oftentimes when you get industrial finish from Europe, it can sort of look like architectural finish in the US. And so different places and different sources are going to look different, so just to take that into place. You guys went at this ad nauseum. As a structural engineer, I think about mass timber as frames and panels. The frames are glulam, these are going to be columns, these are going to be beams, sometimes they're braces, sometimes they're struts and grid shell. And then we've got panels, NLT, DLT, CLT, the micro-lams, really cool, the cassette panels, all of that other stuff. But primarily, we have frames and we have panels. Thinking about spans and proportions for these systems. So like Scott mentioned, like approaching a timber project and kind of just knowing what the right ballpark is. You know, your beam depth, your glulam beams are going to be about 1 inch per foot, as of roughly speaking. So 20 to 30 feet is kind of that sweet spot, as the team previously mentioned, and more than that, you get very deep beams. Your CLT panels, one thing I will say that's interesting about this, if you have odd geometry or if you have interesting beam to CLT details, you wind up having to split your CLT panel at every beam. And when you do that, you get a single span of CLT. When you do that, your upper limit on your span is going to go down. Instead of 20 feet as that rule of thumb, you're really closer to 16, 17 feet for vibration and deflection and things like that. Unless you go to a thicker panel, which is going to add a significant amount of cost. So if you got a single span, 17, 18 feet, you can do a double span, that's going to get to the 20 foot typically. You know, thinking about mass timber is kind of like, right now it's kind of growing, we're going through growing pains. There's sort of a wild west of different products and accessories that we can use. You know, fasteners are screws and nails. And, you know, there's 3 different manufacturers here. Every one of these screws has a different coating that it comes in, a different range of diameters, a different range of lengths, and different capacities that are all based on empirical testing. In structural steel, I've got A325 volts, and I've got A490 volts. And that's it. And they come in any length and, you know, a range of diameters. That's easy, right? But this, to design a structure and to know what the connections are, I have to really specify that. And so in addition to specifying the CLT layout, the CLT species, the glulam, we're finding at Thornton MSA it's the best interest of the project to fully design and detail all connections as part of this. If you leave that up to the manufacturer, the GC, then there's going to be all these questions and it's more likely to be a bust. That increases the responsibility on the design team to coordinate that and understand how that impacts the budget and thinking of procurement, but it really is the best way to control it. Similar story for connectors, and I am saying connectors very deliberately here. A connector is a proprietary product where the capacity is based on empirical testing. It's manufactured whether it's raw glass, essentially strong time, light tech, whatever, what have you. By comparison, there are connections. And a connection is something that is not proprietary. It's something that's engineered, and the still be an efficiency. There should be an efficiency in it. It should be simple, easy to understand, easy to fabricate, easy to install. But it is for sort of engineered fit for purpose, right? And you're not pulling something out of a hat. And what that allows you to do is understand what the variables are. If something goes wrong in the field, how does that affect the capacity, et cetera. So again, you can also, if you do these right, you can tend to get them for less money per unit than some of the proprietary products, because again, the proprietary products are owned and are off the machine. So, here. The other thing that you can do with connections versus connectors is have more control on fire protection. This one for the Ascend project has a piece of wood that goes in there to conceal it. That wood also provides fire protection to the steel elements of the connection. So controlling that configuration and really help with the conversation with the authority having jurisdiction on what's the fire rating of a connection. Michaela talked a little bit about this, but connections between CLT panels also very important. She talked about that. I didn't get into that very much. Pat talked about this, about SHAR. I'm sure you guys know about this, but it's specified in the codes, so it is something, again, that we can calculate on every project. We don't have to rely on a black box. But you design a member for a reduced cross-sectional area, because in a fire, whether it's a 1 hour fire, 2 hour, a certain amount of the material is going to turn to char, no capacity, and you have some capacity left. When you do this, you're not really over-designing it. I don't like that term. I'm sensitive to that term. What you're doing is designing it for a different condition. We don't care how much the beam deflects in this case, right? So the beam can sag quite a bit as long as it doesn't fail. Also, you assume people are getting up and leaving the building, so you're not designing it for the same live load, fully occupied live load, as you would in a non-fire case. So you're reducing the beam size, but you're also reducing the criteria, and you're reducing the loads. Acoustics and vibration. I'll get into this in a project example I have a little bit later, but suffice it to say, especially in residential, transmission within a space, transmission between adjacent spaces is super critical. Getting all the details right is important. You guys saw this in a previous slide. Another one. What this has, and I know that again this is a little bit of a sensitive subject, but we have the European suppliers here as well on the right, and just making sure that what are your project goals, right? What is each project trying to achieve, and what is the time frame, and at what cost, and talking to everybody, right? And that's what we would encourage. If you are interested in remaining local, and that is the number one criteria, don't talk to people, right? But other projects can benefit from getting a range of things. Vertical shrinkage, I won't talk on that. All right, so now what I have is a lot of project examples, most of which are TTs, and few are others, picked for purpose. I'm going to start with some structural projects that really have exposed structure. This was the Canadian Pavilion at Expo 2020. Toronto office did this, and this is really a semi-structural facade on the pavilion. What I like about this, it's pretty sure it's a cedar product because it's exposed, there's no coatings on it. It's designed to age naturally in the desert environment. I also like that in this image, what you can see is while the final condition feels like a grid shell and it's like a 3D structure, in fact, there is a primary, a secondary, and a tertiary load path. And that comes up a lot in timber structures. Creating grid shells is incredibly difficult. Creating continuity across multiple members is more difficult because of the way that we design connections. So thinking of members as primary, secondary, tertiary is really valuable. So the primary ones here are vertical, then you have sort of the diagonal running from the lower left to the upper right, and then you have the infill going the other direction that completes the structure. This is another one we're working on with Studio Gang in Hudson, New York, the Shakespeare Pavilion. This is a kind of a fun one because, again, we have primary structure that looks like a grid up top. We actually have primary structure running sort of upstage, downstage. We have secondary structure between that. We're using the micro lamp plywood product on the top in order to form fit to the roof curvature, right? So if you think about CLT to form it to this geometry would be incredibly difficult. Would be impossible, but it would add to the cost. So we're using a different product, a different roof diaphragm here to facilitate the geometry. Well, fun fact on this one, this is a structural catwalk. The cables and some struts here actually helping hold up the roof. That wasn't intended, but once we looked at it in the model of how it behaved, we decided to take advantage of that. This is another cedar project. Another cedar project, the Moynihan connector. This connects the High Line to Penn Station and the Moynihan Mall in New York City. Another, like I said, cedar project, exposed wood. And this is really where you get into that concept of connections, not connectors. So you can see here the wood members are working in axial at the Hewlett truss, and the connections transfer those axial forces and distribute them around to different members. What I like showing here too is because of all of these factors that we're trying to synthesize and create an optimal structure for, weather exposure, structural engineering forces, connection detailing, the visual appearance. One of the things we wind up doing with timber structures quite a bit is including renderings in our concept documents to help basically communicate an idea. And sometimes that rendering winds up being wrong. Michaela will come and tell us that we're stupid or can we do it this way or whatever. But if we hadn't gotten that out there, if we hadn't put our idea forth at that level of detail, we wouldn't have thought that until it was too late. This is a project that opened up about a year ago in Memphis, the Sunset Canopy Atomic Park right at the Mississippi River. We have a series of these 6 steel quad pods. And again, we have this sort of grid of timber elements. 4 foot deep, 10.5-inch wide glue lamps, spanning up to 130 feet. And this also, I like this one because it drives home this sense of primary versus secondary. You would think of a gridded structure as being a two-way structure, right? There's as much depth and structure in both dimensions. In fact, the way that it behaves, because of the geometry of the quad pods, you have a very clear primary load path with 4 continuous members basically spanning across the activity core, and then you have individual members that, this is the moment diagram, sorry, I'm not engineers here, but the magnitude of the area is basically the amount of work that each member is doing. So you can see here you get your primary members, 4 of them connecting the quad pods, and then the secondary members, you can see the quad pod layer with the boxes here. So what that allowed us to do is simplify the connections, so we're not transferring moment across every connection, essentially. Similar to Carl's comment about looking closely and seeing things, the court looks great from the ground, and the canopy looks great. You look up, it's beautiful. If you start to zoom in, you can see some of the tolerances. Here, some of the offsets between the different members. And you can also see our splice connection. So, connecting a 4 foot deep member that spans 132 feet takes a lot of work here. And essentially, this is a big seated connection. So this member sits on this one, and there's essentially a bracket, a Z bracket that comes in and gets down like that. So this one can bear, the load gets up and bears on top of this. And then this is one of the splices that we also have moment continuity through, where we have holes to transfer the tension and compression forces. We have shear transfer sort of as a backup in addition to the seated connection. And then all of these other fasteners are for reinforcement. So when you have a member that's this big, the code says anytime you have a notch, you have to have reinforcement. Anytime if you want to increase the bearing capacity of the bolts on the wood and transfer the load to a larger section, you can do that with reinforcement. The bearing force on the top of this member, to deliver that down to the member, you can put screws in that for reinforcement. And then because these members are so deep, this is kind of a lesson learned here. They're all treated. So these are all pressure treated members. And they were pressure treated after being CNC. So all of these holes, go back one here, all of these holes that are plugged are essentially bolt holes. So they were drilled out, and they've got a hole that goes all the way through. What you're doing, and there's a slot in the middle, you're increasing the surface area. When you take this, you dump it in a tank so that it absorbs all of that preservative, that treatment, surface area creates more area for that to get in. And then versus the section here that has to be CNC. When you take it out and it dries at a differential rate. And we wound up getting, can't see here, can't see here, great. We wound up getting differential checking through some of these portions of it. And wood checks, and it always has, if you look at the beams in our office, they've checked quite a bit and they're still holding capacity. But in a brand new structure, you want to arrest the check, so we put some diagonal screws into the number to reinforce and arrest some of the checks that didn't grow over the life of the structure. So, very clean connection from the outside. It's almost imperceptible from the ground. A lot of work goes into that. A lot of work. Some residential solutions I can kind of pick up here a little bit. So the project's in Wisconsin. So this is your typical. In this case, it's a 2+5. But you have a concrete podium, a stick-built structure up above with CLT panels. You guys mentioned if you looked into this, the stick-built walls, there's less timber in them. They're less expensive. And then you can also put insulation in them to help acoustically separate the units between. So having stick-built panels as the demise walls and the bearing walls, a lot cheaper than using CLT panels. And the other thing too, depending on contractor preference, it's fairly easy to swap out light frame wood with light frame steel. Of course, a lot more embodied carbon in the light frame steel, even relative to structural shapes. Keep that in mind. But again, if the economics drive the project one way or the other, you have to make that call. Similar project in Muskegon, Adelaide Point, right on Lake Michigan. This is a little bit higher price point, more luxurious market. This one is a panelized building, so this does have both exterior walls, bearing walls, demise walls, and CLT panels with CLT. The veranda here along Lake Michigan is Flueland, obviously not used, but all of the interior walls are. This is not a CT project, and it's kind of a very neat project, a little bit old at this point. But this is the sort of point-supported post slab. This is where you get into some of the interesting benefits that CLT has. It's not quite two-way system. It's not one-way. It's not two-way. But versus DLT and MLT, which is really a true one-way system, you can actually get panels that span their sort of weak axis direction between columns. The span of this is limited to the manufacturer. So if the manufacturer can only do an 8-foot wide panel, your columns are at 8 foot. Works really good in student housing or other occupancies where closely spaced columns are noticed, but it doesn't have quite a bit of flexibility. One benefit, and I'll get back to this here in a second, is you have no glue end. So you're not paying for the glue end. You're not paying for the connectors for connecting the glue end to the columns or the floor to the beams. So you're saving quite a bit of money. Ascent in Milwaukee. Who's heard of Ascent? Okay, this one's gotten a lot of press, so I might go pretty quickly through this. Pat alluded to it here. It's 25 stories. It's 7 stories of post-tension concrete, 18 stories of mass timber. That's not permitted by code. You're at that height, you have to have a non-combustible material. We all know that wood burns. So if you look at the permitting back when this started, IBC 2015, 2018, in wood construction, you could go to up to 85 feet above grade, up to 5 stories above a podium. Right? That's why you see 1+5, 2+5. However, the code has, as Pat mentioned this earlier, alternative materials and compliance methods. And basically, if you can demonstrate to the authority having jurisdiction that the performance of your structure meets the intent of the code, they'll let you build. But that's jurisdiction by jurisdiction, trigger by trigger. We did a 3-hour column fire test to help kind of demonstrate this at the time that the project team as lead. And essentially what that allowed us to do is instead of being, we still went in as a type 4 structure, but the jurisdiction allowed us to use the limits on story height and building height and number of stories for a type 1. So all of the other sort of concealed space requirements of type 4 had been met, but just the overall I'm not going to get into this, but obviously the code has come a long way since Ascent. So 2021 made great strides forward. 2024 has made even more. You go up to 12 stories with 100% exposure. Typical floor plate, typical construction system. So this is a post and beam in Blueland. You can see our beams generally run in one direction, except that our balcony openings here. 20 to 25 feet by 16-foot base. Skip the construction video. Mass timber, a lot of you guys mentioned smaller construction crews. This building, when it was priced out competitively with concrete. There's a lot of concrete construction going on in Milwaukee at the time. It's not a huge labor market, it's a big labor town, so labor is expensive. And the crew size needed to build a mass timber building really helped make this project competitive. So it was cost neutral, it didn't save, it didn't cost more, but that was a big defining piece. We talked about coordination, obviously MEP coordination, it needs to happen early with these in order to fully take advantage of the manufacturing, the CLT, you've heard that today. One of the things that we structurally offer, and this goes back to what I was talking about before, is something called advanced timber delivery, which is a fancy way of saying we do technical models of timber connections as a service, so that these connections can be modeled at the same level of detail as mechanical systems. And we're seeing that maybe 50% of our projects accepted, and other times it's just sort of like, well, we'll figure it out later. So finished products, you can see the beams, the CLT exposed ceilings, etc. Big jet time, right? 4 minutes? Okay. We did another project here. This one, the C40 competition in Chicago. I don't know if you guys are familiar with that. Assemble Chicago, it's called the Studio Gang. Another project, except this one used a hybrid system with CLT floors and essentially straight-in-place CLT formwork and cast-in-place concrete beams that carry the load in the final condition. What this allows us to do is have longer spans and without impact on the floor. You can see here in the building section, we've got another sort of cast-in-place concrete podium. There's a YMCA, the basketball court down here, and then we've got our timber structure up there. The other benefit of this system, similar to the point support, can't see that, sorry. The other benefit of the system is you create a beam that gets placed at the top of the slab, and you don't have to add another Blueland beam to save the Blueland, you save our assembly is on hold due to some funding issues. The Edison in Milwaukee, same system, very much moving forward. So this is 30 stories. Again, it's about a 7-story concrete podium with mass timber above that, and we're using again this hybrid system. For some of the purists, I'm glad that Pat has left. Some of the purists will note that we have gone to a concrete slab for the core area. A couple of reasons for this. It helps with the efficiency of the concrete forming on a 30-story building. The efficiency and the ability to move vertically is a big part of the economics. And also, these are where the kitchen, the bath, and the floor spaces are. So you're not exposing any of this timber. So taken together, we are looking very closely at low embodied carbon concrete for this to help offset the switch from timber to concrete. But again, trying to balance all of the different project goals. This is what the system looks like, sort of as a concept, how it gets built. You put your columns in with your anchor rods. You put in your stay-in-place CLT formwork. You do shore it, but you're not shoring the whole floor, you're just shoring the beams. Put your CLT on, place your concrete, finish it to the top of your a set line in your anchor bolts, and then place your next story. So I got another few slides here, and I'll go through these pretty quickly. This is a project in Detroit, confidential project, but looking at all of the different systems and communicating the benefits and the challenges with each system. So here, same floor plate layout. We looked at post and beam. We looked at the hybrid concrete beam. We looked at plate and panel system, and then we looked at that point supported column system as well. Communicating that with renderings, communicating that with section cuts, And then, generally writing reports, giving a sense of, okay, what are the proportions? How do these spaces feel? What are the, what's the piece count, right? Michaela talked about how many pieces am I picking? What's the volume of timber down here? This is the embodied carbon, piece count, and these graphs down here are the volume of fiber. You just get a sense, a takeaway, okay, what do these different systems mean, again, for the other metrics? And it's not just about, oh, I've got a timber system and it prices out. Really drilling in and finding the optimal system. Commercial and institutional, you guys just showed this one, another one in Under Armour HQ. You guys did mention this, but you got girders beams in one direction only. If you want a 30 by 30 foot bay, you want to exceed the span of that CLT, you're going to introduce this intermediate beam with off column lines, so now your skin becomes a lot busier and becomes a lot harder to route any. So again, one of the things we like about this hybrid system that we're looking at, this is a 10-foot panel and a 40-foot panel. And we can do this in about 24 inches of structural depth as a hybrid system for a typical office space. So again, it's a 40-foot by 20-foot grid. You get a lot closer to a Class A office, which is still important in certain markets. Project in Stockholm, again, thinking about how different cultures look at mass timber. This was a project we won a competition with a hybrid steel and timber frame, very low floor heights in order to build European cities. The overall building height and architectural incredibly important. So maximizing that floor-to-floor height, like the number of stories that we can fit onto the site, very important. So we looked at sort of a delta beam or half channel system. One of being too much steel, and one of being too much cost. This was right around the pandemic when steel prices went through the roof globally. So we looked at different systems. We looked at a single beam, a double beam, and again the hybrid system. And there's a trade-off, right? Column spacing, depth of structure, all of that. So how do we convey that? We convey it with renderings, right? So we had this. We had a system that we're used to in the U.S. for the Class A office space. We go to more columns, bigger columns, deeper beams. We can shallow that up if we go to 2, and we can shallow that up even more if we went to the hybrid. And again, looking at system depth, system GWP, global warming potential, the weight of the system, the amount of quantity, comparing that all, and the client ultimately picked the alternate 2 with the double beams. I'm going to skip through all of this, manufacturing facilities, data centers, again, communicating some of this at the early phase. I do want to talk about labs really quick, and this is where I'll end. Vibration is a big challenge for mass timber. One of the biggest design criteria for lab is vibration. We have sensitive imaging equipment, diagnostic equipment has very strict vibration criteria. But it's also one of those spaces that benefits the most from biophilic design, with institutions who have sustainability goals. How do we get timber to work in a lab? This is the Discovery Partners Institute. It's a competition we did. We did not win this, but a lot of really interesting research came out of it that we evolved through. We looked again at a typical concrete floor slab, common in laboratory buildings. We compared that to sort of this banded system, and this was really an early version of the hybrid that we had, a little bit deeper and narrower on the beams, which we later realized was the right choice. But what we found is that we can get with this system pretty generous proportions, 33-foot span, 22-foot base. We could get ECA design criteria for pretty much the whole thing. And that's really your desktop microscopes and the bulk of your imaging. We found that there were areas around the facade and toward the core where you could get B, which is even better. It's an order of magnitude better. And depending on how you laid out your lab, you could have some really high-performing labs in this space. We've carried that through. We've got a College of Medicine where we're looking at sort of using the radial grid, double beam, to really cut down on the CLT span to get higher performance for higher performance in each phase versus the other. And then this is a project at the Root Institute in Portland. we are looking at, again, this is just our modeling. What we're doing here, this is a little bit more sophisticated, and not every owner goes through this. But we're actually looking at very specific walking paths and saying that, well, if you're not walking straight up the middle of the day, you're only walking on a corridor, the spaces where your sensitive imaging are maybe less effective. And we're doing that to come up with these heat maps and saying, look, most of your floor plate, you're getting these spaces. And that is all.
Thank you, Nate. I'd like to invite Adam Smith, our final expert and panelist for the day. We're talking about projects that he has formed, Synecdoche, Ann Arbor, and now soon to be in Detroit for up to. Adam is working on a unique project that's pushing, it's a housing project. It's pushing the limits of building code acceptable in Michigan, and also a big proponent of Michigan legislature to incorporate the IBC 2021. That, I'll let Adam talk about this project.
Thank you. Okay. Last one. Yeah, I'm Adam Smith. I'm the director of design for Synecdoche, which I also went to Illinois Tech, and myself and my partner Lisa Sauvé, started Synecdoche. Most of you are seniors. Started Synecdoche our last semester of senior year, and we did our first project together that we found on Craigslist. You know that? Just take it yourself. This was 2009, so there was also a financial crisis happening. There weren't a lot of architecture jobs at that time, graduating from school. We were both going to go to grad school at Michigan the next year, but we really didn't like sitting around and doing nothing or working in offices. So we started our own thing, found our own project in Detroit, and actually built it during our graduation week, really. I don't show it here, but it's just, you guys can also start offices now. No need to wait at all. This is our office now in Ann Arbor. We're 5 people. I don't have a map of where we're at in the globe or where we're at in the country, because we're just here. So we're just 5 people, office in Ann Arbor, but we have a studio, and we have a physical shop space as well, where we have been, since that first project where it was a very low budget, it wasn't going to happen if we didn't build it ourselves. So we got very intimate with how to build things and how to actually put things together on a very tight budget, making the design actually come out and using that time to keep designing while we're making things, which was really important to us, and is still really important to us. We operate a 4x8 CNC router in this space as well, and like you said, we're about to move all this to hopefully we're under contract to purchase a building in Milwaukee Junction. We'll be moving all this to Detroit next year, which is exciting. But over time, we've been making either custom, working with a lot of small businesses, starting up their first business for the first time, and then working with them to create spaces in a lot of existing buildings, and doing custom fabrication, like for the front of a bar counter, or in an office space where it's the feature desk when you walk into a law office, into hospitality spaces where there's no wood at all, and we just use whatever elements we can get our hands on, designing breweries and campuses and beer gardens. But today, for what I want to talk about today, is kind of our carbon handprint of what we're working with. So you've heard a lot about carbon footprints, but I want to think about this as carbon handprint, what you actually put on and what your work is going forward, instead of just what our embodied carbon is, but how much can you actually give back. A lot of the projects you work on may not be a mass timber project to start, especially small budgets or small projects or houses or retail spaces. Not everything is going to be a big mass timber project. That's well, I'll show some, but I want you to be able to use that kind of, how do we use that thinking of carbon sequestration, of using biofuel design on very small projects that are not big structural projects. I didn't put this in the right order, but I'll get back to that. So these are 4 projects I'll show, the kind of extra small, medium to large scales. The first one being an early project that was only 100 square feet. It was a competition for a 10 by 10 pavilion that would only last 7 days. So similar to this pavilion here that's temporary, that at the end of this will get reused and into another form. We knew that building a temporary pavilion, it can easily just get thrown out, right? All that material, if you don't plan it out right, a lot of it will just end up in a landfill. And we wanted to divert that. So we found from a sawmill that makes hardwood boards, they cut the edges off of every board to make a dimensional size for a hardwood. And this was something that they all had one similar dimension. They all had 1 inch of dimension, and then they vary in width. Some are like 3 inches, some are as small as half an inch. So how do we use these pieces that are just going to get mulched up and kind of intercept that process? So we take them for a week, make a thing, and then give them back to the sawmill. They mulch it, it goes right back into the process, so there's as little waste as possible. So we designed this kind of stacking system that would go 10 feet by 10 feet by 20 feet tall. And we ended up doing it without any fasteners at all. There's only a tension rod at the top corner, so it holds it all down in compression. But we stacked a few thousand sticks, I don't remember how many. But stacking all these created this effect that you couldn't get with, just with aligning everything perfectly. Every layer of this was really just Lisa and I on a forklift feeling out how the design was going to come out. We knew the effect that we wanted, but we let it kind of work in kind of a raw method, like we saw it in the stack at the sawmill, and let it be in place. The next one, kind of sizing up, this is I'm going to see this project for the final time tomorrow. This is in Milwaukee, Wisconsin. So I don't have all the final images of this, but this is a project for a body piercing studio in Milwaukee. It's only 1,000 square feet. It's a small retail space this is how it started off as, just an empty space, and a lot of, again, using the same thought of the life cycle of the project. Retail spaces might last 10 years, like in a good retail condition, and then end up like this and be demolished and taken apart and put into a dumpster, and all that stuff goes away again. So we wanted to use the opportunity of this space with not a huge budget, so we didn't want to affect like things like the ductwork or things like the fire sprinklers. So how could we use materials that were recyclable, that could also be built in this space? We're also working with the building codes that we have to work with. So we planned out a couple floating piercing studios in an office and left most of the space pretty flexible, but decided to go for a method of using cardboard tubes to make the walls instead of metal studs and drywall. So reducing the amount of carbon intense build out, even though this is a very small project, it doesn't really make a dent in the world. It's just a small method we could still use those ideas of mass timber that we're all talking about every day in your studios to apply it to this. So we have portions of it that are built by the contractor on the site that have plumbing and cabinets, but then we actually, as a shop, built all of the cardboard tube and plywood components for the spaces. You see, as it goes through here, some of the health department rules we have to work around, or it has to be a smooth, cleanable surface for the interior of the piercing studio, but the exterior doesn't have to be. So using both plywood and the tubes together make for one rigid wall type. This is what using the recycled material to do it. This is an initial sketch of like how the assembly would come together. Very simple, just to 2 pallets of 8-foot long tubes that are made every day at a place in Wisconsin, actually, that are made out of recycled paper. And then this is one of the first mock-ups. And we're talking about also prefabrication in the scale of buildings with CLT and glulam. This was a small version of prefabrication where we made panel sizes in 34 inches wide and a couple different corner ones. And then we're able to then work with a contractor in Milwaukee who's doing one thing, and we brought them out one weekend and installed them. So we're cutting most of the ribs and pieces in our shop, making the support system. Like I was saying, in Milwaukee, they're building the posts that would hold the walls so they meet code, so they're not touching the ceiling, to hold the walls enough so they don't tip over. And then we packed up all of those pieces, brought them there, and physically installed them in place. And it only took a day and a half to put all the walls together, going from basically no rooms to 3 rooms in that time. It gives a different effect of the space, right? Just thinking about what different materials you can use. If we're talking about paper, we're talking about tubes, we're talking about the softness of that space, and kind of changing the idea of what a piercing shot would be. It's not so much a harsh space, but it's more of a ritual of enjoyment and making you feel comfortable when you go into the space. Was the ultimate goal here. This was before all the lighting had been completed, but it was the last time I was here. So it's coming together, and hopefully it looks good tomorrow when I go and visit. So as we scale up now into more what we've kind of been talking about today, how like we, as a small design studio, we're pretty flexible in what we take on, where we'll go from that very small project to very large projects in the matter of an afternoon. This is actually a project in Ann Arbor that's an infill project on a property that I also own this property that we'll be self-developing this as well. So this would be for an 8-story building that's 28 units. And thinking about the team presented the Portland Airport this morning and talking about the carbon sequestration of the building and the roof. And I had to do this quick calculation just to put in perspective how much carbon was sequestered in the buildings. One flight from here to Portland on a 737 with 535 kilograms of CO2 per passenger is about 100,000 kilograms of CO2. One flight. This one building that I just showed you, an 8-story, 30,000 square foot building, if we did it all CLT, it's only 590,000. So it's 6 flights. So three round trips. Just put it in perspective of how much is being put into the atmosphere every second. So that's why I say we don't have to just be like just cutting down to 70% of carbon. We need to go the other way. We need to go negative and go the other way and start regenerating. Otherwise, we're just going to keep just kind of chopping away. So this building, sorry for that, but it's kind of the emphasis of we should be applying this in every single project we do. This building on a property is a very small property that we own in that little green triangle there. It's a small infill site in an area of west side of Ann Arbor that's been recently upzoned to allow for more density in that area. I used this site last semester. I teach a housing studio at University of Michigan, Talbot College, where we also take on housing, and we primarily use mass timber in all the projects. Design blocks around here, so you can see from the difference of density that could happen in this area that is now just a straight commercial space with 1-story big box stores, lots of drive-throughs. There's 12 drive-through banks along that street, so it's pretty rough. And you see this red area is all the underutilized land that's mostly parking, mostly associated with parking. There's barely any buildings there, and all of this now has been upzoned to allow for much higher buildings, much more density. this is, I threw this on as well. It's a tool that you can use to kind of evaluate your materials and the carbon and what's actually in the building. It's from the Office of Periphery Architecture from Finland. As we've heard a little bit about Finland, Finland is really moving forward in research and has been doing so for a lot longer than really we have here. So this is a great site where you can kind of work through different sizes, really basic information about the building, change things like the structure, the type of structure, the columns, and see what the effect is on the overall carbon capture of the building. If your intent is to capture more carbon, then you need to use more wood. So using posts and beams wouldn't be if that's the outcome you want, you would not use posts and beams because, well, this one's storing 247 kilograms per square meter. Post and beam is only storing 57. So it's a huge change between those. And with this tool to check out, you can put in your different sizes and you can start to see what the effect is between those choices and quickly see how it feeds back on your basic line and design. It's worth checking out. But with this project, our aim here is, as Michaela said earlier, to bring rectangles. It's a simple site. A rectangle works best on this, and keeping housing affordable too. We need to keep things simple, right? Construction is really, really expensive. There's been a lot of talk about wood construction being more affordable. You have to be extremely smart to make that affordable. Because in this area, there's not a lot of experience. In Michigan specifically, there's not a lot of experience with this. So with this version, we're looking at, or you're thinking about when we've been learning from Michaela and learning from other manufacturers about what spans work best with this, and how can we design housing that actually uses those spans as the spaces that you create. So in this version, we've designed it to be just CLT supported floors. So we have a 13-foot span between those, and then we have another one going north to south that makes up the cores of the building, so that it opens up and keeps a more flexible floor plate, and as simple as possible, stacking everything together and making it more vertical, not really changing anything in this design, but making the environments inside enjoyable for things like balconies, and you're playing with that space of going to be outside. But then when you have that simple space where you can use the simplicity of it and you have the material like paint already. We used to say a lot of don't paint with different stuff or don't even paint with materials. You have already the textures in the wood itself to make a space beautiful. And so this is with this being 8 stories, this would be a type 4 C building in Michigan, which not yet is allowed by code. I'll touch on that in the next project, but we're almost there. We're almost approved. So the big project that's kind of been the impetus to learn the most about mass timber in our office is this one called Southtown, where this is a 225,000 square foot, 215 apartment unit building on an entire block in Ann Arbor, the kind of south side of campus, athletic campus area. This one was the start of talking to our building officials about what the new codes are going to be and how we could work with the 2021 building code before Michigan formally adopts everything. So we've been talking to our building officials for the past 3 years on this project, which is key to being able to, now we've submitted for building permit, even though Michigan does not have the 2021 building code right now. But they understand that what we've been going through, they've been coming to mass timber events. They've been learning from suppliers. They've been going to conferences from our small building department, and really being able to back us up when we're talking to the clients on this. We've only proposed mass timber on this project. We've never been any other option to do it, to do any other structure. And really this client is pushing us more as much as we're pushing them, honestly. And I'll get into that next because this little blurb down here, right? This is 225,000 square feet, and we're generating all of the electrical power on site. We're not connected to the DTE electric grid at all. So it's an islanded microgrid, and I'll get into that in a second. But this is where it's located, just this block here on the, just to the left there is the Michigan Golf Course, Phillips Arena, big houses off to the left. So it's right in a really great spot in Ann Arbor along transit corridors, which also included, made us not include parking, right? Just reducing the amount of trips that people have to make also reduces the carbon intensity of a building, even though it's not built, right? It's not a built thing, but putting something in a space that has mobility is better for the environment. Originally designed, the main impetus was to build basically a building on top of a park. We knew it was going to be a concrete podium, and we wanted to give that concrete podium space to be a park. So up on a park with two main access points, and then a building basically placed on top of that would be all timber with more connections that cut through it. So in the process of design, thinking of it as really a wood building on a concrete park has led us and connected us all the way through the entire process. Like I said, we're using the 2021 IBC, which will now be the 2021 Michigan Building Code, which has been submitted to JCAR, which is Joint Committee on Administrative Rules. If you want to learn about how slow government goes, it's been sitting there for a while. Now we're just waiting on it to move to the next step and get voted on. But we've been both presenting in Lansing about this and backing up the codes. We tried to push it to get 2024 things in it, but they're a little skeptical of new things. So it's a little slower. But I say that because the people in the room are open to hearing anybody's opinion, especially people in the industry, especially architects and people working with it. So if you want to, these codes are not static codes, I guess is what I'm trying to say. They can be changed, and they are being changed. And they need people in the room that support it more than people who don't support it. Because people who don't support it show up. People who support it usually are pretty quiet. So go to open rules. I'm going to skip that one. But basically, what I said before, if we're looking at reducing carbon intensity and going the other direction, we have to think about the building outside of its structure and outside of everything that's built, but how it's being powered. So this building, instead of being on the DT electric grid, it's completely islanded using renewable natural gas as its only fuel source. And we're not burning that natural gas. So this is actually coming from the client who's creating an entirely separate business inside of the ground floor of the building to make an energy utility in the building. So it's going to be running by the way, just background, this came in. We talk about like working with manufacturers and coordination along the way and keeping that going. This came in at the start of CDs. Would have been great to have this as a design element the whole time, but that's not how it works. So this is where we are. And the more we've kind of dug into it, the deeper the client has gone. So we're going to go further, we're going to go further, we're going to make it even better, which is a testament to them that they're willing to go this route. No one else, honestly, is. So what we're running from is these three large fuel cells that make electricity by separating the ions of natural gas. They have a heat output that we're using now to recapture and use for all the domestic hot water in the building, and whatever else we can use extra heat for. We're still figuring it out. We have a lot of heat. So that feeds into a control system that is managed by these large battery storage systems that are, all of these components are about 30 feet long by 12 feet tall by 12 feet wide, that have huge clearances that have to fit into this building. Along with rooftop solar, along with electric car charging, there's 50 car spaces, geothermal units, and everything has to work together in this. Like, there's not one thing that's operating independently. Even the cars will charge up the batteries when if the cars park there and full of electricity. Making this go into a carbon positive region. So we're going from this chart. The red here is what DT Electric, their current carbon intensity is for the electric grid, and then with their markers of what their goals are supposed to be moving forward in the future, compared to Southtown, which is initially has to be run on natural gas, which has its own carbon intensity. It's not the cleanest, but it can transition to hydrogen when the price of getting hydrogen fuel to the site actually works out. We've looked at it, it's just, while this is expensive, that seems too expensive. So as we move down that road, Southtown will be will be going the other direction in carbon intensity. And even in this, we're recapturing anything that comes off this fuel cell exhaust. We're recapturing all of that exhaust into a carbon capture system that turns it into liquid CO2 on site. We also have a 30-foot tall silo that's shown up on the site that will fill up every other day and be trucked up. So the amount, while this is a very low carbon intensity thing, the physical space of a huge volume of liquid CO2 will be picked up every other day to make electricity. Now that then goes and gets sold to beverage companies and bars for things. You need your soda and water and you need CO2 for other things. But just to see it is going to be crazy. What it also does by being off of the electric grid is that this is looking forward for other projects in the world. This is a resiliency method that when the grid, there's problems with the grid, we've had plenty of problems with the grid in this area. As anybody lives around here knows, right? Wires above ground break. Utility grids break. And they break often. And there's a lot of problems with that, where this is a moment where when electric utility grid is down, this doesn't have to rely on that anymore. So all that's to say, that's all happening. The vestibular is also there as well. As the simple part of the building is basically mass timber. But moving up the building is designed as these kind of one podium that's one big plate, and then as we go up, it's separated into two separate buildings, so that you have these different spaces of a park on the podium. It doesn't feel like an enclosed space. And thinking of it in a simple method, like this is two bars, two rectangles kind of together with one more diagonal across the center. So even though it has this unique design and character, it's still in its bones thought of as two very simple things. And as we move up the building, it terraces back and becomes two separate, taller structures in the edge. Kind of looking around it in EXO. I just dropped these in to show what, we work with a structural engineer out of Vancouver called Aspect. Again, we've had no experience with building a big building like this, especially out of timber. So we specifically looked for structural engineers that had a lot of experience, and Aspect was our choice. And this is something that you brought up about mechanical systems fitting between columns, right? The beams in this building are pretty deep, right? To get to that 2-hour fire rate of wood for a residential building, the beams really get big fast, and we need to also move ductwork, fire suppression pipes, electrical, a lot of things along these corridors. Because in this building also we're not using your typical HVAC system in each unit, where we have ERV, energy recovery ventilation coming from the roof and through all the hallways and into every unit, which is not super typical in a residential building either. Looking Aspect worked with us on the carbon intensity. This is the embodied carbon of Southtown with the against the other methods, so we can see that it is better in that sense, but it's not perfect, right? There's still a lot of concrete. There's a lot of concrete that are in the floors of the slabs. And this is the look at what embodied carbon is, right? This is how much you build in one building is 49,000 flights from New York to London, right? It's a lot of carbon we're still emitting when we're building a building. But when we're operating this building, that's the goal, is that this building will be around for 100 years, and it's going to operate carbon negative. Overall, it's got a lot of other things that work. But getting a view inside of how we showcase the timber and use it in spaces where we have a pretty dense structural grid across this, but showing it in every space we can, getting as much daylight in as we can for every livable unit. So there's no spaces without daylight, there's no bedrooms without daylight. But also when you're on the podium, it feels like you're in actually two separate buildings. So you're getting a sense of instead of one massive structure, which it is, you get this breakdown of two different structures across the spaces and on top of the podium, where the initial intent is still being kept through it, but it's just two buildings on top of a park. This is while all the code, all the energy systems, everything still has to flow through and finish with that same idea. So overall, even though this is an extremely large building, we talked about mass timber all day, I still go back to that first project where we're just thinking about material, how we can use it and not let it end up as waste in the end. Using a bio-based material, making it feel good, and using it for our own enjoyment. It doesn't just have to be like sustainability. It doesn't just have to be for numbers and on a spreadsheet and to hit targets, but really it should be for us to just enjoy. We're in buildings all the time. Just enjoy it, and making it more sustainable allows it to be more enjoyable. So that's it.
What was the facade material of the upper floors in that last one?
It's going to be a rain screen that is from Ceraclad.
Okay. So it's like a treated wood?
It's not a treated wood. No, it's more like cement tile.
Oh, cool.
But it also has a funny property where it collects any NO2 from exhaust from cars. It sticks to that facade, and when the sun hits it, it breaks that NO2 down. Anyway.
I'm gonna ask you some questions.
Yeah. It seems like magic, but it's really cool.
Thank you, Aaron. I'd like to invite Scott, Nate, and Michaela for our last panel of the day.
You need me too?
Yep.
Oh boy.
Questions?
I do kind of have a question. It might be a little bit off topic. Maybe this is, Carly can tell me if this is out of bounds. You can tell me if this is out of bounds. Someone can tell me. So it's just something I've been thinking about a lot. So as most of you guys heard, because I talked about it earlier, from Portland, which is a little crunchy, it's a little granola-y, it's pretty talk about sustainability a lot and everything. And I've been also teaching a little bit at the University of Oregon, which is very sustainably focused, but we talked about sustainability a lot today. And we're all architects and structural engineers and developers, and we make our living by building things, but I'm really coming up against this more and more. The most sustainable thing is to not build. So I don't know where y'all go with that, but I was especially thinking about exactly what you're saying, we need to make these things sustainable throughout their life, but the most sustainable thing is to use the context we already have. And I was thinking about a project, I forgot who presented it in the first section. We've been a student group, maybe not, but it was in Brooklyn, where it was a light frame steel building that then had those pods inside. So I don't know if any of the panelists want to talk to if you all have been struggling with this also, and you've been talking about it in your sectors.
Yeah, I can just make one comment on that. So, well, there's two. Might be So, yeah, I think that's like one thing we always try to teach. And my background even more so is in sustainability than it was in wood products before I started. Lots of life cycle assessment, all of that good stuff. And so that was like a hard pill to swallow, I think, for a lot of people that I was working with. And it's like very, very clear that we should use what we have. That's always the best thing. That's the same thing with automotives. We're so excited about electric cars, but it's still way more sustainable to use the cars we have on the industry today. Hard pill to swallow sometimes, but that's again where mass timber can be a really exceptional material. It's light, it's flexible, we can cut it in many different shapes as we've been talking about. So we have a project right now in Florida, which is a historic preservation project, where all they could save from this building was the facade and the exterior structure, which was great because they did. They chose to stay there. Even the roof was totally crumbling, which was to our benefit because we're just picking panels over into that building and dropping them in. So we're building some structure within glulam and CLT, but they are trying to utilize as much of the building that was salvageable. And that team really, that was the architecture team that drove that. They were gonna tear it all down and rebuild, and the architecture team said, no, let's find a way to use as much as we can. So I think as long as we're starting there, mass timber is a great opportunity to do that because it's lighter, because we can make it into different shapes, because when we go field verified dimensions and they're never quite what they say they are, we can cut it, right? So that's one thing for that's positive, hopefully.
I mean, we do a lot of work that's adaptive reuse, and I've got other projects obviously that are outside the purview of this. But on a personal level, I live in a suburb outside of Chicago. It's not unlike Detroit in that it has 130, 140-year-old building stock. It was built very quickly. Some of it's too big for its intended use. It's way past the end of its useful life. The folks who lived there in previous generations did not have the resources to maintain the buildings because they were required a lot of maintenance, a lot of time, a lot of money. So I think even if you look at keeping our current building stock and just making sure that it doesn't fall down on people, right? Or it doesn't, we think about operational or things like that. We're going to have to build buildings. So there's just not enough existing building stock that is fit for purpose for today and for the future. That is the only way I can sleep at night with in this career, but it does double down on we have to come up with really good design that uses less, improves the quality of the space, longevity of the space. So I've worked on a lot of projects where we tried to keep it, and it wasn't good enough, right? The building wasn't suitable for so it's a distraction. Not really. It's kind of skirting your question.
It's an impossible question.
Yeah.
I mean, there's one point, like, if we're going to be building, we have to be specific about where we're building and who lives there, like, how we live there. So instead of, like, for the infill project I was talking about, that area is all upzoned so that you can have living there. Instead of developing more suburbs out, right? We have to think about where we're going to build. So it's not really in the building industry. It's like from zoning, from planning, from development, from, being able to develop cities more and get more people into denser areas than what we've been doing.
Yeah.
So this question was for Scott. It was about the building that you first talked about in Mexico, where you're actually doing an expansion on that main section of the building. You said was in phase 2, and I'm not sure if phase 2 is happening or if it was just like something you guys were designing for. But it was kind of piggybacking off what you guys were talking about. If you guys do that expansion, are you able to reuse any of the panels that are on that north facade? Since the facade would be extending out again for that second phase?
Yeah, so the future expansions are entirely dependent on the growth of the home appliance market. So please keep making more apartment buildings so people can buy more stoves and refrigerators. radius and other things. But yeah, the intention would be for that north facade to be dismounted, move 300 feet to the north, and be reinstalled. It would look a little bit weird, at first, because you would have this sort of aged facade, and the two short ends would be new wood, but eventually it all, weather and look the same. But yeah, definitely the idea would be to move pieces around. That's one of the things we talked about with the engineering team is, once you put a fastener in, you can't take it out and put it back in the same place. So then how would we maybe place the ears and the other connections, in a different location, but still maintain the structural capacity of the panels for that second placement. They're not infinitely movable, but 2 or 3 times, probably yes.
Hi, so piggybacking off of those 2 questions, wondering if any of you have encountered in conversations with a client or in your practice, talking about the eventual deconstruction of mass timber projects, and one, how do you talk about that with clients, or it's just like, well, this is what will happen 100 years from now, and like, how do you factor it into how you develop your projects?
Yeah, how do you plan? Like with so much of the structure diaphragm being concrete on top of the CLT panels, I know there are products available and there's structural systems available that offer more demountability than others. How do you
Well, I mean, mass timber is another great one to design for deconstruction, right? Like it is heavy pieces of timber that are connected with connectors that can be unfastened pretty easily. We right now are not at the phase where we're deconstructing a lot of these buildings yet, right? So there's amazing research from the Forest Products Laboratory. There's lots of forensic engineers that are going out, figuring out ways that we can, better check in on these buildings while they're built, to make sure that the wood is behaving and nothing is degrading. There's all of this kind of work first and foremost to keep these buildings as long as we can. And we do know that there's precedent of like 2,000-year-old wooden buildings, right? So we always start from there, is that this is a very durable product that should be thought of to last longer than just the typical 40 to 60 years or whatever we want to say there. But that said, we're always looking at ways that when these can be deconstructed, tested, because that's the important part, is like, okay, that certification, is that still valid? Is an engineer really going to trust that certification afterwards? No, but we can do machine stress rating and do additional testing on these products to re-put them back into buildings, or if that's too tedious and too expensive, we can put them into different markets. So for us, we can put these back into the industrial markets and start using them as matting, even with the concrete top if it's still there. And then that can be used for the next 5 to 10 years in our rental fleet of CLT mats. And then from there, there's all, like I said earlier, there's all of these different secondary and tertiary markets for wood. So that part is much easier, and because we're trying now, at least right now, not to put too many coatings and yucky things into these into these timbers. It's the same reason on our industrial side we don't pressure treat anything, because we want that end of life to be more sustainable and to have more options. So that's the way we've been thinking about it, but I think time will really start to tell. The Netherlands has requirements for deconstructing of all of their buildings. The city of Portland has requirements for deconstructing all their buildings. I get so many people say, Michaela, please put my deconstructed lumber into your CLT. It's a great idea. It's a beautiful idea. There's so many people that have done it. You have no idea how much lumber it takes to make a CLT panel. It's not scalable. It's just not scalable. But there are a lot of other really great scalable opportunities, like if you could do the machine stress rating and verify the design values of deconstructed lumber, NLT is an excellent product to reuse lumber. because you're doing that labor on site. You have a lot more flexibility. There are markets for this, so there are so many amazing researchers out there doing a lot of great things that I think over the next 30 to 300 years we'll start to see what we're gonna do.
Actually, that NLP point, they are looking at Georgia Tech.
Yes, they did.
When I was at Lawrence Georgia, they put a call out to all the lumber yards in the Atlanta area, collected the 2x6s,
Yep.
and I've got them smoothed out and went through a kind of custom shop NLP on campus and used that as the first floor start.
Yeah, and it's so beautiful. I love that. That project is absolutely gorgeous. Sorry.
No, I have two non-answers again. So. But I shook my head when I said we're the engineers have to trust it. And the one thing I want to emphasize is that wood does, the properties change over time. One of I own a 2-flat apartment building and it's 120 years old, and a girder or beam supporting floor joist deflected, it's got a curvature about 1/100, depending on, it's supposed to be like 1 over, or span over 300, so it's got a lot of curvature. Me and a couple of my structural engineering friends, we tried to jack it up and we built this wall underneath it, and it let's say it deflected about 2 inches over a 12-foot span. It's a lot. We got about a ½ inch out of that. And then as we continued to jack it up, rather than having that extra 1.5 inches come out, we just lifted the beam off the end. So it was permanently deformed into a smiley face. It would not go back to a straight beam no matter how much force you put on it. So, I mean, wood, you put it upside down, a big camper, right? Yeah, camper. But wood does change over time, so the deconstruction is challenging. A little bit of again, an antagonizing answer here, but in the couple of conversations I've had, and I work in a lot of institutional buildings, so probably a little bit harder to pull apart because of the robustness of them. My sense has been that the premium it would cost to make the building last longer and be more flexible for unforeseen future occupancies would be less costly and less obtrusive to the present day occupants than designing it to be deconstructed. So how can we make our buildings last, 500 years until we can suck all of the carbon out of the air with, fusion? So I think we have to buy ourselves that time. Taking the buildings down, I think, is a reaction to how we built 50, 100 years ago rather than how we built today. I'm open to counter argument.
Well, I was just gonna add, like Pat mentioned these carbon credits or carbon markets. So one of the things with one of the carbon markets, Aureus Earth, they require the buildings to be designed for 100-year minimum lifespan. So I feel like the wood industry actually is speaking differently about how long we expect these buildings to last. So I think even that initial intention is just so much better than a lot of industries that are like 40 years, whatever. We'll tear it down and throw it away and start again anyway. I want to make more money,
Or 8 months.
Yeah. Oh, well, that's the big thing is developers. We talk about upfront costs a lot. A lot of people are like, okay, well, it's all about the upfront costs, but we got to talk about operating costs. Like, no. These developers do not care about their operating costs at all, and that's not an equation that they even start to consider. So you also have to we need someone, yeah, I know, it depends. Unlike this might be more architect developers. Anyway, there's a lot there. but I do think thinking longer term is just a really good gift to this industry. So hopefully that'll help.
Yeah. So just a comment about the previous point on using your flexibility and the issues we can use if you want to use it in load-bearing elements and all the complications. What about thinking about reclaimed wood in terms of moving it down the structural path, maybe using it as siding?
Oh, for sure.
That might be non-structural or tertiary system, things like that.
No work. Yeah.
Yeah.
And I don't want to say that you can't use it structurally because there are a lot of structures out there. I think it's more Michaela's point about converting old timber into newly engineered products is not necessarily compatible. But there's plenty of uses for old wood that
And I have a question about this is about Neil's information project issue. There was this beautiful curved ritual with curved ruler, and then you mentioned there was a micro CLT that you bent into the shape at the root system for that ritual. So my question is about the construction process for that. How did that happen? Um, was the glue lamp CNC, and then on site the micro CLT was bent into, or it was steam bent?
So that project hasn't been built yet. The design intent is the glue lamp is going to be curved as part of the layup. And so again, there's a primary, secondary, tertiary systems. The primary glue lamp is curving, I'll call it upstage and downstage of the area, and that's curved as part of the layup. The infill purlins are actually just straight segmented numbers between that, with cuts angled so they fit in. And then the micro lamp was selected over the CLT, so yeah, that it could be bent down like steel roof deck. On some of these airport roofs or large roofs that have complex geometry can be, can be field bent and laid down and just fastened into place. I would imagine that with the wood products, you are probably CNCing the perimeter to once it's bent, the warped geometry would then line up with the next piece. Whether you're doing that in the shop or in the field is a conversation with other folks. But yeah, the specific product was thicker than traditional plywood, but thinner than CLT so that it could be field bent.
I have a question. So mass timber right now has a lot of variables, cost, appearance, species. And do you, and I look at it and compare it to the electric vehicle. And now they've been around, there are issues with lithium coming to the forefront from supply chain standpoint, and now there are some pockets saying, well, the hybrid car is the way to go. Using that analogy, you see this the concrete side of the equation, steel guys, they are upping their game where you're having carbon sequestering concrete, the iron reinforcements being replaced by polymers or carbon meshing, and they are saying that our concrete that way is not coming close to mass timber, but if we take together, it's a better product. This is more for you, Nate. Take part in competitions and do the experimental systems. Have you encountered or researched anything of that nature?
Definitely. So I showed that project with Mr. C40, and what we actually won the competition with was a traditional cast-in-place concrete building. And we looked at hybrid steel and timber. At that time, Chicago Building Code would not have allowed for an all-timber building. And what we found with cast-in-place concrete by talking to concrete manufacturers, they really got like the fear of God in them with mass timber and sustainability, and it caught them by surprise. And all of a sudden, they were doing trial mixes for 70% cement replacement, type 1L cement, and all of this stuff to cut embodied carbon by 70, 80% in concrete. And again, when you look at the economics of it, and a project needs to actually get built, and it can get built with one system and not with another economically, concrete really upped its game. Steel, I think, is a little bit behind. A lot of U.S. steel, it's 90% recycled, electric arc furnace in the U.S. Cold form steel, so composite steel deck, cold form studs, much lower much lower recycled content, higher embodied carbon. Same thing for HSS tubes, very high embodied carbon in HSS tubes versus roll shapes. So I think, a lot of the talk about mass timber is in residential, which has traditionally been a concrete dominated system. I will say we have a contractor we work with in the Chicago area, Adjustable Concrete. They have started a mass timber division. They said, we're great carpenters, we fly forms all the time, we know how to work with these systems, and we can pour the concrete topping. And they basically said, we know how to do this. And if somebody wants to build this building, we'll help them build this building. If they want to build a traditional concrete building, we'll help them there. So I mean, it's really, that's the approach we take, is we're somewhat agnostic. So tell us what your goals are, and we will help you meet those goals, right? So I think if certain industries do not want to up their game, then they will be relegated to certain uses. You know, steel will, I mean, it's a great material, but it will it will be long span, right? Or it'll be pre-engineered buildings or transfer trusses for a 20-story tower, wherever you can only do something with steel. But so I think knowing what the materials are, knowing what your market can get, and what your client's goals are. It's just you gotta keep your options open.
I think Adam said one of the most important things is we have to be pretty radical in every material to bring down the embodied carbon of our construction. So I love the idea that mass timber may have lit a fire under their butt. Like 5 to 10 years ago, the concrete and steel industry was just like, it's all gonna burn, and they were just like coming at us so hard, and it was like that fear. And now it absolutely has totally changed. They're like, oh wait, no, maybe we'll up our game. Oh wait, maybe we should go see what this is about. We should add this to our portfolio. He's talking about adjustable concrete. Now they've got adjustable timber. I'm working with multiple installers who do multi-trades. A lot of the cold form steel guys are like, oh, I know this stuff. I'm just going to start doing CLT too. This is super cool. I just toured our facility with the local iron workers union members. And it's not like they're, before maybe it would have been like, we're checking out the competition. What are they doing? Now it's like, oh, we want to do this too. They're going to get a mock-up. Like they're going to get a mock-up for their facility to learn how to build with mass timber because they know it's coming. And we all know it takes all these materials. Nothing's ever going to be 100% wood. It's just not going to be. It's not going to be 100% concrete anymore. It's not going to be 100% steel anymore. We really need to challenge each one of these materials to do everything they can to bring down the embodied carbon of their materials, make them more durable, make them last longer, and then we all need to work together to make better buildings.
To that point, back to your point too, I'll give it to you just a second. But with making better buildings, I think we need to make simpler buildings. Like we've gotten into the it's very highly engineered envelopes that we deal with, and coming from Finland and seeing just mass walls, mass wood walls with no insulation on an exterior wall, and then being happy with it, but meeting performance criteria instead of prescriptive criteria of our code here, where we're held back when we have to input a lot more material into something.
I think has been demonstrated by different people's projects. There's always going to be a place for hybrid systems, but we're not making new limestone. We're not making new sand. You want to use concrete, they're vacuuming that sand up off the floor of the ocean. They're burning limestone to make the raw ingredients. But trees grow so goddamn fast in the forest. I think when I went to Austria, they were like, we can grow a new single-family home every 42 seconds or something ridiculous. So there's a Swedish-Finnish forest products company called Stora Enso, and their motto is the future is in the forest. And they do CLT, they make paper, they do all kinds of stuff. But I really like that motto, that the future is in the forest. And wood is the only renewable building material. Everything else is sort of one direction. I agree. Steel is. There's a lot of recycled content in there, and that's great. But I think we do simpler buildings, longer lasting buildings, more durable buildings. That's where we need to be. A totally not CLT building is but one that I think about a lot is the cathedral in Los Angeles, designed by Raphael Moneo. It was designed to last for a minimum of 500 years. So who knows what air conditioning systems are going to be like in 100 years or 200 years, but they planned extra space so they could get to all those systems to be able to make those replacements. And the way we build buildings now, we pack a bunch of shit up in the ceiling and it's hard to get to. So we have to think about how we route our utilities and how we place those systems so they can be, swapped out as time goes on.
Let's see, where to start. Nate's detail that he showed when I was standing in the back looked like a circuit diagram more than an architectural detail.
The dovetail thing?
The two beams that came together with all of the splices and
Oh,
joints
oh,
and
yeah,
rows
yeah.
and like it was amazing. And I even saw a student take a picture of it, which I was very happy of. And I could imagine there could be an entire lecture about just that detail, or you might have one. It was amazing. You guys also just brought up the fact about like having a mock-up built or having a prototype built. We have the capacity with the studio that the students potentially maybe with you after we come to visit the thing, we have the capacity to do mock-ups within the studio. So I'm curious if between all four of you, are there particular details or aspects that might be worthy of prototyping for the students to be thinking about?
Well, I sell a lot of mock-ups. We give a lot of mock-ups. We sell a lot of mock-ups, mostly for training purposes. We always, so Woodworks, which is a trade association that supports the mass timber and timber industry in general, they do a lot of trainings, like on install, and it always involves these mock-ups. So they have an initial one that has some really, really great details with it. Every manufacturer has done their own spin on it. And then we've worked with like Rosa Bloss and Simpson, and even the local iron workers, just like a custom steel connection so that there's multiple different connections within those. But yeah, there's like, I would say Woodworks has a lot of great materials and support for this stuff.
I have a question. I'm going to pass it to Scott because I had a question for you during your presentation. But going back to like my neighborhood and houses, I was in town a couple weeks ago for the Center for Advanced Manufacturing Summit, and it was super cool. Oliver David, I forget, there's a
Woody Creek.
Yeah. So he's got a prefabricated intelligence city. They use a lot of prefabricated panels and panelized systems. Element 5 has some of you guys talked about it. So a lot of those intelligence cities have huge capital costs, right? They have like a 10-year, like probably what you guys have on Ceres, like they have this huge cycle money keeps flowing in, and it's gonna be a long time before they're profitable, right? And so where do we get, when I think about a mock-up, I don't think of something we build that is maybe less proprietary than a full system, but that allows us to deal with the labor shortages that we have for different types of construction. So I'm going to pass it to Scott. You talked about prefabricated wall panels that use 2x8s. What about 9 5/8 inch engineered wood joists? It's like all things like that. So I would say prefabricated wall panels.
One of the things that always comes up in our projects when we're talking about how to control costs and quality is reducing trips around the building. So if you do a regular, stud wall frame, somebody puts up the studs, another guy comes back and puts up the sheathing, someone else comes up with the air barrier, somebody attaches on the windows, then you do your continuous insulation, then you add your, let's say it's a brick veneer, you gotta do your veneer, like it's 6 trips around the building. And so how can we do this in ways that, reduce those pieces, and even if it's a wall assembly that's multiple elements, this can be built in a factory under controlled conditions. You can work 3 shifts at night, you can do it in the rain, you can do it in the snow. It improves the quality and reduces labor. I think for that office project, it didn't make sense to do the walls in CLT. That's why we looked at a dimensional system, and we looked at how it could be prefabricated, because our client was coming from a precast sort of baseline. Can we make it in elements that are roughly 10 feet wide? Those, I think we made them 7/4, so like my Mexico project, you could fit in a container, but lots of different ways to come at a prefab wall system using dimensional lumber, using I-joists, using engineered timber, other elements.
Yeah, on the hotel project that we did, it's just like all mass timber, but literally for blast resistance, they don't care about anything else. It's amazing. Lots of sequestered carbon. Holy cow. So that project was all panelized. We did panelized walls for all of that to really help on site because they had a big constraint for labor there, specifically because it was on the military base. So you have to be a U.S. citizen. I cannot tell you how many truckers called me and said I can't get on this base. And so that limited their labor pool too, right? So we did panelize all of the blue lamp stud walls for that project.
But that's now the third, like in the panel, 3 of you have talked about the role of labor. So how would we simulate, even Scott, for you as an architect, where you may not have access to those things. So students working on their projects this semester, and you guys may say a different factor, like 60 to 70 to 80% of the construction cost is probably labor. And if detailing can change that, or the prefabrication can change that, how would a student that doesn't have access to that be able to be simulating that or thinking about that? Or should we just bring in a set of GCs at 80 points in the semester?
Every single architect and engineer needs to hang out on a construction site and actually put these things together. It is so important. I can't tell you how many engineering details I've seen. I'm like, have you ever held a screwdriver? Like, or, anything. Like, do you know, like, oh, I'm not talking, I would never talk about TT that way. That is not a TT.
I think the most important
so important.
Would probably be the spline. No one thinks about, like, to make a solid wall, you're not just letting these up, they spline together. So how do you turn the corner? In our building, we've got a lot of air leakage and that's also acoustic. So the spline is probably like the dumb, but like motherly detail for wall.
Yeah. The corner is always
the corner problem.
But I would also think about fabricating, since you're gonna have, it's a different scale if you're fabricating it in your shop here or in my shop versus your shop, right? You have a much larger everything. So I would also challenge the students to think about the timber not in the way that you see it, but in the way that a sculptor would see it. Think about it more volumetrically, maybe. What example, Howler Union Architects from Boston, Eric Howler is one of the partners. They just created a sculpture, I think it's in Washington.
It's that's the thing.
Yeah.
Are you really curious how it's going to last the weather?
That's why it's out there. But thinking about it more like stone carving, it was actually carved by people who are extremely skilled in stone carving and 3-dimensional stone carving. So it's using CLT and glue that with mass timber in a completely different environment than what we've talked about today. So I would challenge that side of fabrication as well, something that you guys are already pretty skilled at. What else can you actually explore with these small materials instead of your typical, CLT can drill a hole in the panel, put it into the corner. How can you try out these things?
I just want to go back to Carl, your comment about not having access to labor. That's kind of the whole point, right? I mean, the part of the popularity of dimensional lumber is you could have 2 guys who could build a 50-foot tall building because it only takes 2 people to frame a wall and tilt it up. So the idea of, okay, if you have 2 people and as long as you have the space, you can lay down a 20-foot by 7-foot panel or something like that at that scale. You fabricate it on the ground inside or on sawhorses. You put the weather resistant barrier on there. You put the rain screen on there. And then yes, you think about how 2 adjacent panels go together. That's the point, is how do you do more with less by doing it inside? And then if 2 people can they lift it, how much does it weigh, right? Can they tilt it up? So, I mean, to me, that would be the thing. If I were an architecture school, that's what I would do. But, and then I would probably try to put it on a machine and break it and see how much load it can take.
That's the engineering.
Yeah.
I think maybe another way that students could come at making a mock-up is rethinking the sequence of assembly. In an American residential stick-built building, we rough frame the window, and then we attach the window to the sheathing with nailing flanges. In a Swedish home that's made in the factory, they start with the window, and then they have a neoprene seal that goes all the way around, and they build the wall to the window. Much higher air barrier, much higher quality. We tend to think of prefabrication or modular construction in the United States in like volume elements. That's why so many prefab homes look like versions of shipping containers, because that's their sort of genetic grandfather. But in Swedish home construction, they build in wall elements, roof elements. They build all of it in the factory. They still need to seal up joints, on the job site. But a crew of like 6 guys can enclose an entire house in like 3 afternoons. Whereas if we do it the American way, like people are even if your studs are coming out pre-cut from the sawmill, somebody's still like nailing them together, 16 inches at a time. And so even in a commercial building, we have a rough opening, then you put an aluminum window, and then you put a fat bead of sealant around it, some shims, and so maybe by rethinking the sequence and what you put in, you can increase the building quality, you can increase the prefabrication, you can reduce the number of parts and pieces, and the number of people that need to do it. It doesn't really answer the question of like how can a student start to think about labor costs necessarily, but I think by bringing in construction partners that might be able to give guidance on that, that would be really helpful.
Kayla, I have a follow-up question for you. Like, where have architects kind of come up against like pressures for like tool tabs, for example? I remember doing a whole thing like if you cut a door opening out of a CNC panel, that's gonna have rounded corners, and your tradespeople on site are chiseling that out. Or like if you have a solid CLT wall, how the light switch get on there? Like think at that scale, because not everything you can do in the factory. Like unless you want to flip the panel over, which is incredibly expensive.
Yeah.
You learn.
Yes.
So you can only build for one
I'm
job.
so glad you're learning that. I'm like so grateful that this industry is talking to architects.
But then if you want to do anything on both sides,
Yeah.
it's probably gonna be cheaper in field, but then that's where labor. With us, it was all the subs, the electrician,
Totally.
mechanical subs, and like that's where the labor is like shot. And if we even thought about where light switches go, then it would be so much.
Well, we have a proprietary panel flipper, so it's not crazy expensive, but it takes time. It's heavy, it takes time. And everything, our factory, our factory was built by a Detroit guy, automotive plastics injections manufacturing engineer. No wood experience, but knows material and knows how to make things go fast with high precision and quality. If you go in most timber facilities across the world and the country, they've been around a really long time. They kind of do things their way. It's more art. It really is. Like every timber facility I've been into is mostly art, not ours. Ours is not art. It is very much how can we get the most precise, most highly engineered, most consistent product off to the end of the line, just like on. So that really gave us kind of a cool way to come about it. And then I'm also extremely lucky to have some incredible architects and engineers on my team that come from, one of our architects came from Benson Wood. So very productized, but she wanted to take that productized, less volume, but more productized approach and not just do, rich people's second and third mountain homes. And so that's why she joined us. But she brought along a lot of that experience where in their shop, all of their BIM technicians, all of their architects are on the floor with their CNC talking to the people that are building those things in there. So that's one really great thing about prefabrication. Again, you're collaborating in the same room. That's awesome. You're seeing it. So that's when you guys are at the facility, like I said, go talk to our CNC operators, ask them questions. And then what we're doing with that information, because I just assume all architects know that because Canvas is brilliant, And she's like, Michaela, I did not learn that in architecture school. I learned how to make pretty glass things, and I wanted to do wood things. But she now has worked with our other architects to put together design guidance early on where we go through all of those things. So we say, here are the tool paths, and architects love this. They like, this is what I love, the feedback. Architects and engineers want this feedback. They want to learn this. Here's what happens when you do this, and I'm going to have to say if this is a chiseled or a rounded corner. Does this matter? And so we're putting actually together an entire design manual exclusively focused on ways you can limit fabrication and still do the things that you want to do. It's not released yet because we're very busy building buildings. That has been very helpful having those conversations from the get-go with our design teams. Because it's true, why would you know about the chiseled corners versus the rounded corners if you don't? And we don't want to have that be a surprise show up on site because that's when the installers do not like you. And I need installers to like me. So we work really closely with the design team early, but there's so much stuff, and always too. All of our design team knows to look at the shop drawings, and if there's fabrication on both sides, that is a red flag. You call Michaela, you call that client, we figure this out. It just takes time. It's all it is. Every second counts. You know, Toyota production control. Every second counts. And so when you have to lift a panel, you have proprietary flipper, flip a panel. I mean, it might only be 15 seconds, but then you have to rejig the panel to the CNC. So now we're talking a couple of minutes. That's a big deal when we have projects that are 3,000 some panels. We produce a panel every 65 seconds. Machining our 2-axis saw goes at about, I think it's like every 85 seconds we can machine on the 2-axis, but the 5-axis CNC only goes as fast as how many passes you guys put on it. Every pass.
Is there anyone doing, like, talk about auto? Is there anyone who would, do this, to mill on both sides, have the panel be vertical for that milling procedure? So you have two robots on either end, do the milling at the same time.
Yeah.
You could, like, have it suspended in the air.
The thing is I love dreamers. We can do anything, but is it worth it?
Make that proprietary.
No, I want to make these sculptures. I want to do all of this. My floor team wants to get panels out as fast as possible. But I think, go visit shops. Go learn about the CNC. You guys have so much more access to this stuff in your studios these days than, like, oh my God, anybody has in the past. It's so cool to see all that. So the more you get involved with it, the more you get on construction sites, the more you pick up an impact driver, do it, drive a screw, figure out what's like. I do all the time. And you're not supposed to for the standard, but everybody, okay, so here's the other thing. This is what engineers hate. Installers are going to use an impact driver even though you guys don't tell them to. That's bad. I should have told you. I know it happens.
It sounds like they don't complain when all the heads start popping on the street.
That happens to our building, is that why? That happens to our building, is that why?
Probably. Every installer uses impact driver. I just want you to know. We've been talking to Vincent about it.
And these screws are like 2 feet long.
So another microcosm of the industry at night. So I built a treehouse over the summer for my kids, and I used structural screws, 3/8 diameter, 5/16 diameter, 6 long. And the first weekend I worked on it, I used an impact. And I came in, of course I came in on Monday, and I told Alejandro about it, and I'm like, and he's like, what are you doing?
It's only because the standard requires you to use a drill
Those
out. are personal based on
not to get technical, it's because nails and screws are hardened. They're extremely brittle. They're not what we think of when we think of structural steel. They're incredibly hard. There are manufacturing processes because they're made all over the world in countries that have better and worse QA/QC. Sometimes the wire that they're made from has hydrogen embrittlement problems, and doing an impact driver increases the heat stress that they see, is likely to lead to fracture.
So now we need to make all of our erection drawings say that, but I will tell you, everyone thought it was.
So no, but hang on a sec. So the next weekend I'm out there and I'm like, okay, I'm gonna be a good engineer. I'm gonna follow, practice what I preach. And I took a drill and I did have to go from cordless to a corded, which I know that's not gonna happen. But I just needed a bigger cordless drill. And I put it on low speed, high torque, and I leaned into it, and it went in way better because the impact driver actually stopped because it has a peak torque that it can apply. There's no peak torque on a drill. Like it's just as hard as you can lean into it. So anyway, I did do it the right way.
Cool guys.
Any more questions?
I just have one question, just for the architects quickly. So we've all been talking about CLT, very structural, right? In terms of replacing concrete, replacing steel. We've talked about its perimeter, we've talked about its core. I think a student group early on said something about erecting a CLT elevator shaft. And to be really quick, I have a story for you. It is not quick, it is incredibly long because of the way they need to be inspected. But because you need to leave it open. Anyway, not fast. But what we haven't really talked about is the interior walls, interior panels. So I think we've all, not all, but we've been talking about like maybe like wood framed or like steel framed, and then one that goes to probably JIP for fire protection. JIP is also not very sustainable. It can't be really reused easily. We're having a hard time like thinking about how to use alternate partitions, especially for multifamily. For the two architects, just for you first, and then maybe you guys have had experience with this as well. Like, have you been thinking about alternative interior partitions, not being stud wall, but I don't know, mass timber is so hard for that as well.
Honestly, I haven't thought much about it, so I'm going to pass it over to the expert.
I thought a bit about this because, like, 2 years ago, we did this, like, as a team, this kind of visioning thing where we just wrote down on a card what we thought a headline would be in 10 years' time or whatever. And one of our interns wrote, drywall and metal studs are no longer used, and we're now in a more sustainable method of demising walls. And we were like, of course, like, why aren't we thinking about this? So it's hard to get past the code implications, and especially in a large building, like a multifamily building, sound and fire between those spaces. But there are, looking out to our other panelized straw walls or clay walls or blocks, thinking about it less so in sticks and panels, but in mats is, I think, the way to start to investigate it. Is it what we started investigating? We haven't used anything applied. Like the first thing we've done is something that's not full partition, doesn't touch the ceiling, but it is the first thought of that. We just completed with paper tubes, which isn't new. It's been used by other people as well. But starting to explore where you can go. And yeah, I don't think it's more mass than it is sticks and stuff.
It's like, where does all the tubing go? The plumbing go? The conduit go?
Yeah.
Is it exposed?
So
like
then you might have to,
15
yeah.
inches for outlet.
Right. You have to think, where are those things? Like in the Pearson studio, we were like, okay, all the plumbing, all the elements are going to be in this one dividing wall that is going to be metal stud and JIP, and the contractor is going to build that because that's the simplest way to just logistically handle that. So it's like very specific about where that happens, so it's less, and then use the alternate method to do it somewhere else. And plugs are on the floor in some spots and away from where we need it, but it's really dependent on scale and type and how far you can push it.
I think architecturally, in terms of sustainability and reuse, that's going to be the biggest one.
Yeah.
Interior partitions and how systems
Yeah.
run through a building.
I think when you go back to the CNC thing though, you mentioned like the MEP, all of that kind of stuff. CLT and like wood panel products that are thicker, like mass timber products, are really not the best wall products. Because routing and, and if we're talking about flexible space and being able to get at any of that stuff, also, if you can build it with 2x4s and 2x6s, like, that's a lot less material and it's a lot cheaper. It's overkill on material when you go for mass timber walls, unless you're in a blast resistance requirement or something like that, right? But I think what we're seeing a lot of is the raised access flooring, and when we talk about flexible space, you can't get more flexible than that. It's not for every project, that's for sure, but we're seeing a lot more of that. And then, no, I think the challenge to the architects in the room is help us find some more products. What are other natural-based products that can pass these code requirements? And I think that is, the drywall replacement is going to be huge coming in here soon. I don't think mass timber is the answer. I do think there could be timber products that are the answer, but time will tell.
I have a question. What's a partition? I mean, why, is there a world where we have demising walls and structural walls? And that's it.
Inside an apartment between two bedrooms, you don't need fire rating there, but you still need acoustic separation. So that would be like the kind of partition I'm talking about.
Yeah.
I do go back to future-proofing our buildings, making them simpler, making them cheaper. My whole business model is creating complex geometry and making things happen that don't want to happen otherwise. Honestly, though, I do think creating infinitely customizable rectangular volumes is a really efficient, sustainable way to provide shelter. My wife is in commercial interior sales, and they just took on a line, a company out of Australia, that it's all commercial right now, offices, but they do reconfigurable rooms. And these are not like the little pods for like, whether it's, lactation rooms or phone rooms or whatever. These are like conference rooms. These are offices that are flat pack, glazed windows, full doors, self-contained MEP systems, VAV boxes and everything. And they're flat packed and they're shipped in the air. Now it's still aluminum and glass, so it's not super sustainable. But to me, that's like you create a structural volume that has the lowest embodied carbon, the best materials, the optimized structural grid, and you just move stuff in and out. Like, thinking about a fixed partition is, I think, what gets buildings sort of quagmired and, oh, this building's not good anymore. Look at that partition. Is it bearing? I don't even remember if it's bearing or not. Call an engineer to remember if it's a bearing wall. So, I don't know. That's just, I'm gonna take it out there because we're at an architecture sale.
Thank you to the panelists. Thank you, Stasha, for moderating this afternoon. We have some wine at the bar. Are you guys old enough? All right, well, thank you to the panelists. Thank you. Great discussion today. Let's continue the discussion and let's have some wine and there's water and cookies and all that stuff. So we'll move there now.